Morning, everyone. As we have the breakfast slot, we're just going to wait a couple of minutes to allow additional people, if there are any, to come in. So we'll get started in a couple of minutes. Cool. Hello, everyone. Just checking, I think I can hear my voice on the speakers. Can everyone hear okay? Cool. Okay, so morning. First of all, thank you very much for attending the 9 o'clock slot. We were worried about how many people would make it. So yeah, thanks so much and congratulations as well for making it at this time. So welcome to Magic Micro Frontends. So this is kind of a story of how we've used micro frontends within our environment. So it's a pharmaceutical regulated environment, how we've used them to help improve some development practices and increase agility. So I'm James, and this is my colleague Nicola. So we work together at Sanofi.
So on the concept of Sanofi, to make also our bosses happy, let's give you briefly our digital mission. So what we want to do is we want to become a leading digital healthcare platform. So how do we want to do it? We want to change the practice of medicine by leveraging data and digital, and to create an inspiring work environment where we can empower people to be the best versions of themselves. So now that we've made them happy, we're going to continue with the presentation.
Cool. So first of all, maybe a quick show of hands, actually. Who here works in a regulated industry, something like pharma or a few? Okay, cool. So we just wanted to kind of explain some of the general concepts, make sure everyone understands what we mean by that. So Sanofi is a pharmaceutical company, which is a really heavily regulated industry. So we're making medication, making drugs that could be injected or ingested by a patient. So obviously safety is critical for us. So we need to make sure that we make the same thing every time. And in our context, working as software developers, we need to make sure that any software systems related to those manufacturing processes, quality processes, work exactly as expected, and we can prove that they have worked as specified, etc., etc. So some other regulated industries, so automotive, aerospace, where clearly safety is really, really key. And another one, finance, so a different context, but where you need to be sure that everything is fully auditable, you know where the money is going, and everything works as expected and is fully traceable. So that's what we mean by regulated environments. In the pharmaceutical industry, just to give a little bit more context, we have this concept of GXP. So we're trying not to use acronyms too much, but we might accidentally refer to it during the presentation. So to explain that, the G and the P mean good practice, and the X is any kind of business domain or business process that we might be working with. So good manufacturing practice, GMP, for us, that's anything related to the manufacturing of medication. Good laboratory practice is how we work in the labs, how we're testing the products. And so we make software systems that interact with both of those processes, actually. So we have this concept of GXP regulations, and we refer to those systems which must follow those regulations as validated applications. So if you hear us in the presentation actually saying validation, validated, GXP, that's what we're talking about. So what are some of the constraints that we have within this industry? So let's say nothing, on the face of it, nothing special, nothing that you wouldn't expect in normal software development processes. So say we have the standards of good development practices, solid architecture. For us, the key thing and what we want to highlight in this presentation is what we need to prove to an auditor. So within these regulated industries, you could be audited at any time. And that means that you may need to present evidence of which version is deployed in production, or which version was deployed in production or official test environments 2 weeks ago, 3 weeks ago, 5 years ago. And you need to be able to show all of the approval chains. So did your quality assurance teams, technical owners, product owners, all approve the promotion to a test environment, then to another test environment, to a production environment? You need to show non-regression testing evidence, so things like screenshots and videos. Everything is really, really heavily controlled. So it's not a crazy idea that you should do non-regression testing or that you should know what is deployed to production, obviously. But the key thing for us is that this can add, depending on how your systems are architected and how your processes are designed, this can add a lot of administrative overhead. And so that's what we're here to talk about, how by redesigning the architecture of your systems, how can you potentially reduce some of that overhead? So let's go back a little bit in Sanofi to look at how we were designing our applications. So traditionally, we would build monolithic front ends. So what do we mean? We have, let's say, some specific business problems that we want to solve. So might be optimization of the release cycle for some medication. So speeding up the process for manufacturing or releasing some medication. This for us would be a single application, monolithic application. We might have another application, so application B, addressing a different business problem. These two are managed and built completely separately, and any change to those applications, so that let's assume they're both regulated apps, release of medication definitely would be. Any changes to those will go through a full change control process. So all of those approvals for promotion between environments, storing all of the testing evidence, non-regression testing for every single component of the app, every release, even if you didn't touch all of those components. And on a bit of further analysis, what we found as well, in addition to those heavy processes, is that actually, although these are specific business problems, we have a lot of contextual data which is interesting for users of both applications, so represented by the different symbols here. So what we found was that although we had separate applications, sometimes there were components or data which was being displayed which was really, really similar or exactly the same thing in a slightly different format between applications. So some duplication of code, slightly different user experience for looking at the same thing between applications. And then importantly for this presentation, more administrative overhead because you're validating the same thing twice or 3, 4, 5 times, depending on how many teams have implemented that. So with this in mind, what is it that we want to do and why are we talking about micro front ends? So the mission for us really is reduce our administrative overhead, be more agile, so help us to release our regulated applications faster, and also build them faster with more control, or maintaining the same level of control, I should say, and also, as a bonus, improve the user experience by trying to make some of those things more consistent between apps which are representing the same thing. Before we go into a technical demo that Nicola will lead, we'll look at a few of the principles, a general summary of what we mean when we talk about micro frontends, to make sure we're all on the same page. So let's say the general concept for us is applying the microservice paradigm to the user interface. So say that concept of small services instead of monolithic services, and using that as components within the UI. So for us, a micro frontend, it's an independent section of your user interface, and it's built really for integration into other applications. So what our approach generally, as we'll talk about a bit more, is where we have things which are likely to be represented in more than one application, it's a candidate to be a micro frontend. And so it's really things which are shared, where we're going to be reusing them, that we would try and build as a micro frontend. It's an independent project. It means it has a separate build cycle, build process, separate deployment, target and process. And that's really important, as we'll talk about for us, because remember that concept of our really heavy admin processes on big builds. Here we're looking at how can we make that smaller, and by making the build smaller, how can we reduce some of that administrative overhead. And theoretically, you can use any UI framework for micro frontend purists. It's not really recommended if you have 5 micro frontends in your app that you have 5 different UI frameworks, but theoretically that is possible. And for us, it's kind of a natural progression. Just the 2 diagrams below that I took from a blog post, but which I think is titled "Why You Probably Don't Need to Use Micro Frontends," but but I like the pictures, so it's all good. So we're actually have already gone through the process of a very similar process on the back end of carving out sections of monolithic backends into reusable microservices. So here we're talking about the same concept in the front end, with the basic goal of reducing the size of our deployments, and therefore the scope of the deployments, and therefore the amount of documentation that is required to go with each deployment. That's the fundamental goal of what we're trying to achieve. And I'm going to give you an overview of probably some of what we picked as the 3 kind of key concepts from the micro front-end world. And then Nicola will do a bit of a technical demo for each of those to explain what we mean by them. So first one should be, applications should be composable. So those shared components, that contextual data which is reused in our monolithic apps, we want to have a catalog of micro frontends that developers or development teams can pick and choose from. So we need to have data X, Y, Z. We'll pull the components into our application, and multiple applications can do that. So by doing that, you're reusing the code. You're also building a more consistent user experience as well. Next one is around loose coupling, isolated applications. For us, the idea is really controlled communication between those applications which are integrated into a page. So the reason that's key for us is, so one micro front end is able to say, you can theoretically integrate me into any application, and that's safe to do, because I know that any data you send to me, I'm going to filter, I'm going to reject messages which are incorrectly formatted, etc. And the other the other concept of the loose coupling is to avoid those applications having to know about all of the other applications which are integrated on the page. So it's achieving controlled communication, but in a simple way without too much integration between apps. And the final one, which is really, really important to us, is the concept of them being independently deployable. So we need to be able to deploy one micro app, a change to one micro app, without having to change all of the other micro apps or without having to change the integrating applications which are displaying them. And with that, I'll pass over to Nicolas.
Thanks, James. Okay, so let me first kill a bit the presentation and let's jump a bit into our UI. So those of you who have maybe seen our presentation in London earlier this year, we had a topic on the evolutionary architecture. Don't know why it died. Okay. On the topic of evolutionary architecture, there we had a small pitch from our millionaire boss, Elon Musk, that wanted us to fly to Mars. So let's say we achieved that goal during that presentation. So we're now taking it a step further, where we want to reach Saturn at this point. So for this, we've built an application which is aeronautical by nature. This means that parts of it should be GXP by nature. So the screen that you see in front of yourself is composed out of 3 micro frontends. I'm going to enter more into details about each and every of these components a bit later. And the application also has 2 routes. So you have the main one, this is the dashboard one, and the second one, which is astronaut running in space. Let's call it a space view. Imagine that we have a drone that just sees something from the outside. So as I mentioned, this page also has 2 micro frontends running here, and more on that in a second. So coming back to the presentation, let's talk a bit about the architecture. So in Sanofi, we're quite proud that we're sponsoring some open source projects. So for this coding demo, I hope that it comes back. For this coding demo, we used Vue.js, which we sponsor, and we used Single SPA, which is a framework how you can build your micro frontends. There are many others on the market. It's just the one that we selected for this demo. So as I mentioned, first we have on the dashboard, I said we have 3 micro frontends, and on the space page we have 2. So the architecture of a single SPA application is quite straightforward. You have a single root config application. That root config application is nothing else than an entry HTML file which registers your micro frontend applications, so which I'm going to elaborate in a minute. And it only exists to create the application. So you shouldn't put any logic in it. It should be like a simple bootstrap file. So what is an application in the concept of a single SPA? So it's the same as the single page application. The only difference being is that it doesn't have an HTML file. I mean, you can have the template files if you're using Angular or something, but still, it doesn't have any HTML file that it builds. And you can have as many registered applications in your root config as you would like. We just selected 2 to make it quite simple. And important concept of an application, since it's being registered, I'm going to show you a code demo in a second. The application by nature is declarative, and it should be lazily loaded. So it shouldn't be automatically loaded on the bootstrap of the project. It should load on a specific activity. So, or in a single SPA world, we call this process mounting. So it shouldn't exist until it's being specifically called upon. And the last concept, and to be honest, our favorite, is the concept of parcels, which you could have seen maybe on the dashboard, but more on that a bit later. So a concept of a parcel, it's similar to the application by nature. The main difference being that parcel is imperative by nature. That means it's called upon when you need it from your own UI. You don't call it upon from your root config file. And it can be as simple as a component, or it can be a full-blown application. In reality, your parcels should be more or less coming from different frameworks. An example, if you use the same framework, which we do here, I apologize. Well, if you should probably use different framework, because if you use the same one, you should probably use the exported components function because it makes it much more lightweight to work in this way. So maybe to show you more in the code how this works, let's jump maybe to see the breakdown. So as I mentioned, we have a root application, which is this Space Explorer single SPA. In it, as I mentioned, we have a index.html file, which provides a couple of things. First off, which is important, we use system.js to load our dependencies. Do you see it correctly? You should. Okay. In it, in the import map, you will see a couple of things. Initially, you will see that we import our applications. We also import our parcels. And we import some shared dependencies. Now we preload some of this data. Again, this is quite bootstrapped. And at the end, we come to the more important part. And this is the basic purpose of a root application, which loads and registers a single SPA application. So for an application to be registered, you need to call it based on, you need to give it a name, you need to call based on its import, which we defined earlier, and you need to provide an activity function. So meaning where this single page application will be shown. So this one will be shown on every route, while the space application will be shown only on the space route. So that means it won't use anything in your browser until it reaches that point. So coming maybe to the next concept that we mentioned, which was an application. In this case, we have two of them. One is the Space Explorer, and the other one is Space. So in the Space Explorer, I'm going to show you the configuration is the same for the other one. You need to provide a couple of things that application can be recognized and that it can properly work. So you have also some utility files that single SPA provides that can help you bootstrap these things quickly. But you need to provide the following functions. In all cases, application needs to have a bootstrap function. It needs to have a mount function and an unmount function. There is also an unload, which is an optional one. We didn't use it in this case. We didn't find it quite useful to show you anything with it. What is important about these functions is they all need to be asynchronous, meaning they should always return a promise that your single SPA knows how to properly handle them. So the last concept that we mentioned is the concept of parcels. So as I mentioned, parcel can be as big as an application or as small as a component. In our case, let's take the Saturn one. This one is at the size of the application. So by its nature, the way you declare a parcel, it's the same as you would declare an application. You again need to provide a couple of lifecycle functions. You have a bootstrap, you have mount, and you have unmount. These look a bit more complex. They're just adding logs that I will use later to elaborate a bit how the application works. So again, it should always return a promise, and unlike how we declare the application in the root config, we specifically mount this one on demand. So you can see in example here, we first need to, how do you mount a parcel? You need to define a slot where you want to have it, and you need to call, now we're in the Space Explorer application, just if I skipped the step, sorry. So in here, we want to call on the mount. During the mount process, we want to mount a component. For it, we need to get that DOM element. And we need to provide to the mount parcel function which parcel we would like to load and in which area of the code we would like to show it. And with this, I will hand over to James to maybe continue talking about the communication.
Cool. So yeah, let's just go through a quick reminder of some of the. Thank you. Cool. of those main concepts and what's important for us. So there are obviously other benefits, but what's really important for us. So first one we're going to look at is loose coupling, the application being isolated and controlling communications between micro applications. So the general concept, yes, we should have things as isolated as possible, but we also want to have good user experience. So there has to be some sharing of contextual data in the UI. So each micro app knows, for example, which filters are applied or if a button has been clicked, etc. So we're looking at how we can control that. So single SPA has a few recommendations of how you could approach this. First one is to export some functions from your micro app, or micro front end, I should say. For us, we've avoided this approach. The reason is because we feel it kind of exposes some of the internals of your micro front end that we really want to avoid doing. And you could potentially have some issues in your application, some runtime errors in your app, if the signature of your exported function changes. So if you change the name of it or change some of the parameters that you expect, it could cause issues in the application which is integrating your micro app, micro front end. Second possibility, second recommendation from single SPA is to use cross micro front end imports. So let's say a similar concept to the first one, but in this case, it's kind of a shared library. So for all of your different micro apps, you have a shared library exporting some utility functions to let you do things like manage authentication between applications. And again, for us, at least in this fundamental thing we're trying to achieve of just sharing some UI state or some simple actions, it's a bit too complex and results in some coupling that we want to avoid. So in addition to the fact that you could have some issues if your signatures change, if function signatures change, if you make a change to a micro app which impacts one of the signatures, you have to republish the micro front end, the shared library, and then anything using that shared library. So you're kind of increasing the complexity of having, you're moving away from that concept of independent deployments, which is so important to us. So the one that we chose and what we'll focus on, and Nicola will show in detail, is to use event emitters. So essentially kind of a pub sub model to emit some events which application micro front ends can choose to listen to. They can listen to them, they can ignore them, they can reject them potentially. So for us, it's really the preferred approach and what we are using for sharing simple UI states. It avoids some runtime errors that could occur if you're, like we talked about with function signatures changing. And it has to be done in a controlled way, but for us, your worst case is that if something changes and your application is not listening to the correct event, you might be looking at potentially the wrong view or the wrong filter within the application. So you have to do this really with care, so you know that you're not going to accidentally show some completely incorrect data for something critical that users need to see. But for us, it's kind of a safe way to keep it simple and avoid those runtime errors, but still keeping some control. And it's you.
Thank you. So for the coding demo, let's maybe first take a look how this is implemented in the UI. So what we're going to show you now is the space view. I'm just waiting for this to blink a bit. So as I mentioned earlier, this is composed out of two micro frontends. You can also see it here on the right side. You have two applications that are currently in the mounted state, one being the space application, the one that you see as a content, and the Space Explorer one. So Space Explorer is consisted out of this navbar that you see at the top and this button Deploy Astronaut in the bottom, well, for me, left corner. So what we did is we're going to emit an event from the Space Explorer component. And if I clear this a bit, you will see how it goes. So from the application Space Explorer, we're deploying an astronaut, and the components, or another application Space, is at this moment handling this event. And you could have seen that we triggered a UI change where the astronaut just moved and came closer to you guys. So how is this implemented? Let's maybe quickly see it in the component here. So in the application space explorer, the main one where the button is located, like I said, there is nothing special here. You just have one button which has on click event, it emits on click event deploy astronaut, which basically is a new custom event. We can use the regular events. We just use this one because we want to provide some contextual data to the other component. And the one thing that you can notice here is that we're providing two things. In this case, we're providing the name and surname of an astronaut, while in the console log, we just caught the name, meaning that the contract isn't actually respected, and it's more of a problem that also James will jump into a bit later. And I can show you a bit how it works on the space component, where in its application, basically, there is nothing happening except when the component is mounted, it adds an event listener, it listens for the same event, and from the detail, which we emitted there, is just passing in the name, which we're just logging, and we just set the state that, okay, at this moment, the astronaut is deployed and you cannot deploy it anymore. So maybe back to James to talk a bit more on the next steps for communication.
Cool, thanks. So yeah, as we mentioned, we've used event emitters as a lightweight and it's a scalable solution as well. So we're using browser events. So any application which is integrated can listen for those browser events or not, depending on how the app is designed. And for us, it's really the best way to avoid coupling between front ends. That's kind of opinionated. So obviously there are other ways in the single SPA documentation. There are other ways that you could imagine, but for us, it's one that works. The drawback for our current implementation of this is that there's no built-in contracts of what events you should be sending, and no real built-in validation, so that you obviously saw a very naive version of it where this poor astronaut is just deployed when someone randomly clicks a button without any kind of safety checking. And yeah, this for us is kind of a drawback. So as some next steps that we're looking at, first one is looking at how we can export a types library so we know, so we can essentially define a contract for the messages that a specific application expects to receive. So as I'll say parent app, but an application which is integrating several micro front ends could have a documented, recorded way of knowing that they're sending the expected messages or broadcasting the expected messages. The second one, as I said, it was a naive implementation of it, but what we want to do is have a really robust way of validating that the incoming messages are valid. And this is actually the more important side of it. It's inside the micro front end, validating really strictly that the message I've received is a valid one. It's, I don't know, the parameters are as expected, the data structure is expected, or the values which are given are within the range that I expect within the application. So this is the key area that we're focusing on now. And the final one that we didn't mention, but is a little bit of a change from what we've been saying, is so far we're talking only about event emitters, but what we're looking at is how we can use URL parameters for filtering, because the URL parameters are accessible to all micro apps, and it's probably a better pattern for us to use, but we're not using it yet. So something that we are exploring. So next concept, we already looked at composability. So how do I, sorry, you have a question? Go ahead.
A couple of questions actually. How is the thumbs up model avoids a runtime issue? The event and the triggering and the listing happens at runtime.
Not without validation and contract in place. It won't avoid it completely. So it avoids it in a sense if your parent application starts emitting some event and you don't subscribe to it, you won't have any runtime issues. But if you subscribe to the same event and you expect something that you don't get, or you get something completely different, you're going to have it. So this is what James explained. So for the next steps, we need to have some contracts in place between the micro frontends that are going to be shared among the teams, so as an interface of communication between them and how they're going to integrate one with another.
How do you create a shared event bus between every micro front end component if you have different framework, or even in the same framework? I do not understand how is the event bus created.
We're going to talk more about the team topologies a bit later in the presentation, if this is...
Is your question about team structure or about the technical implementation of the browser events?
How is an event from a package, let's say an NPM package, emitted, and another NPM package is being listening to it? How is the event bus created so that they can actually publish and subscribe to the events?
So this is where the root application comes into place. Everything is coupled together there, so everything is bundled. So when you emit an event, it's a native browser implementation. So at this moment, you emit event to the whole, everybody who listens to it. Doesn't matter in which application is it. Is it a React, or is it a Vue, is it Angular? If it subscribes to a specific global event listener, so the one that you have at the window, you're going to catch the event. So you can have multiple subscribers in this case even.
Because I was concerned about the concurrency. If two concurrent actions cause the triggering of the event, then if the browsers handle it, and not the application.
Yes.
Thank you.
No worries.
Cool. Good questions. Thank you. So yeah, composability. So this is the concept of being able to assemble small micro front ends into a larger application. And I don't have very much to say on it because it's all in the demo.
Yeah. Okay, so the next thing that we're going to take a look into is the parcels. So the thing that you could have seen earlier is when we mount this, you can see that the application, once this page is loaded, as I said, this has 3 micro frontends running. Well, at this moment, only 2. One being the Space Explorer. And you can see also, maybe looking back, that the space is not mounted here. That means that it's not accessible at this route. And here, where the crew manifest is not mounted, we are imperatively going to call it now. So we want to call upon the crew manifest to appear. And you can see that the event was the mount function was called from the Space Explorer micro frontend, and the parcel crew manifest caught it and finished the mounting. So with this, let me show you maybe how the code looks like for the mounting of the. Sorry, 1 second. It's in the Space Explorer one. Here we have on the. Oh, sorry, wrong component. Here we have a button, like I said, that has a button pressed. It follows the same logic. Basically, on button pressed, we're going to either, depending if the component is mounted, we're either going to mount it or unmount it. Mount, it's the same as I described earlier for the one in the parcel Saturn. So you can see that we need to provide the DOM element where it's going to render. We provide a function that imports it, and we send the DOM element. And we update the crew manifest state at this moment. For the unmount, you will notice that during the mount, we store this in a local variable. And if you want to unmount it, you can call upon it, you can just call upon the function unmount, which again, it should be a promise. It returns just true or false. The component is then unmounted, its life cycle is updated, and we update the crew manifest state. The implementation you saw earlier, again, it's the same one as in the parcel Saturn. We have just a bootstrap function, mount and unmount, so nothing spectacular is happening on the parcel that you haven't seen so far. So coming back to the presentation, is why are parcels important to us. Okay. So parcels, as you could have seen, we composed a UI, which was a dashboard. Okay. And it was composed out of various elements. In our case, we used Vue for all examples. In reality, you shouldn't do that. You should have one, maybe if it comes from React, the other one from Angular, maybe third one from Vue. But as James said, probably you shouldn't mix and match so many things. But as you can imagine, at Sanofi, it's a corporation quite large in its size with multiple development departments. And we have a diverse portfolio of applications where each web application can use a different framework. And as you can imagine, we're present on the market for quite some time. So we had a couple of evolutionary steps which we need to integrate together. We need to refactor some things. In our department, primarily we work mostly with React and Vue, but I can swear that we don't have anything else in our portfolio. And as you could have seen earlier when James was showing, we have a functionality overlap between the applications where different business cases have been resolved multiple times by different teams and basically creating a variation in the user experience for the same subset of data or same subset of services. So the teams unintentionally created functionality duplication and in some cases even code duplication. So as we had some experience with working in microservices and creating some, let's call it business data sets, so we already separated our data, we separated our backend services, we restructured the way we work, but the only thing that remained was these monolithic front ends. So in order, you cannot just say, let's use parcels and everything is going to be magical. We had to restructure our teams a bit. So we created something like a pod-like structure where we had enabling teams working mostly on these, I apologize, transversal applications like micro apps like we saw here, like this Saturn or a crew manifest, which you can import in multiple applications that would use it, be it a GXP or non-GXP alike. And we had the product teams mostly focused on the business value, so delivering business products to our customers, and they were responsible for integration and domain-specific functionality. So the two teams just had to interact with each other. So for this, we just composed some interfaces where one is providing to another, okay, this is what this is what we delivered, this is how you can integrate it, and as James said, we're now exploring the ways how we can document this more in a better way. So far, we're mostly on a, I don't want to say paper-based, but Confluence-based documentation in this case. And maybe jumping to the next step, which is being independently deployable. And I think this is the part which is mostly interesting to everybody working in a validated environment. So what does this mean? Micro frontends by default benefit from being independently deployable. You can easily migrate, you can easily experiment with it. And we're going to talk in this section a bit more about how we can independently deploy components and how we can share dependencies between the components. So let me show you a quick demo on how this works. Let's jump briefly into our browser. And let's take a look back into the Space Explorer page, where, as you could have seen in the extension that I use, we have two micro frontends, Space and Space Explorer. At this moment, they are both mounted. And in our root configuration, we just declared them. So the application running on port 3000 is our root app. So you will see that nothing changes here. The time is still the same. But let me just quickly deploy an updated version of Space Updated, which is running on a different port. Let me quickly copy it. Okay. And we can, in a development environment, quickly override the Space. And if I'm not mistaken, it's JS app.js. So here we have a red rocket, and now we want to just apply override. And without even changing the root application, you just independently deployed a new Space application, something changed below it. So at this point, you can imagine that the space application was GXP. It went through all its quality processes. You have every following documentation, but the UX for the users changed without any deploy being changed on the root config or on the Space Explorer application. So maybe this was an ugly demo, so let me show you in a bit different way. Let's clean this up and return it to the initial state. And let's just jump back into the terminal and quickly kill this one. And I'm going to kill the main space application. And I'm just going to readjust the port so that you see of a space updated. So you're going to see that nothing changes except the port where it listens. And I'm going to redeploy just this one. It should run on port 8083 now. Yes, I hope it's visible. And if we take a look here, it should refresh. If you take a look here, now we have, again, completely independently deployed, so you have the same URL, nothing changed, but a completely different application running under the hood. And this is actually the main benefit that we want to present to you, and this is how we solve this, let's call it a big issue of how to accelerate our delivery in a sense of a regulated environment. So next topic here that I mentioned briefly was shared dependencies. So if you remember when I talked about the root configuration, in the index HTML, we had a couple of things which we shared, and we imported with System.js. We called upon a single SPA, view, and view router, and we provide them to all applications. So to configure it, you just import it, and in applications where you want to use it, you just need to configure your Webpack that it uses externals, which are view and view router. So to be honest, you can, and you don't have to use shared dependencies. We find it quite useful that we use it, especially since we reduce the overhead of loading same things multiple times over time. This way we increase the performance. And I don't know if I have, no, yeah, that's on the shared dependencies. Again, if you have different frameworks, maybe you want to add also React, but as a good rule of thumb, I would say you should try to just load large dependencies and share them, while the smaller ones you can probably load at the level of the application. So why do we find independent deploys so good to us? Well, they're easy, they're quick to set up, they work by default, they allow us to share the dependencies between the application. And one thing that we haven't touched so far, and it's quite important from the quality perspective, and that's testing. So with this, we keep the testing capabilities of each micro app to the team, or micro front-end application, to each team that develops this one. So at this moment, you only unit test, test integration, you test the end-to-end at the level of the application that you're developing. And at the moment when you integrate it, you only test the integration between those two applications. You don't have to retest the behavior of the application below it, the one that's integrated in it. And I'm going to hand over to James.
Thank you. So yeah, a quick wrap up of looking at what we've seen and some additional problems and challenges that we've had. So maybe to summarize, it is a really nice approach in our context. It's working and it has helped us to improve some processes, but it's definitely not without its challenges. So a few of those, so things we didn't already talk about. First one, I think, is the learning curve. So for developers. So first of all, understanding the concepts of single SPA or generally micro front ends, the overall overarching principles. It took a little bit longer than we expected for everyone to, ourselves included, and we're still learning, but for everyone to understand those general principles before getting to the point of being able to actually go ahead with the technical implementation. And then when you get to the technical implementation, it's a little bit more tricky to get started than we had anticipated. So if you're going to go with this approach, make sure that people are in an environment where they have time to learn those things, where they don't have the pressure to deliver something really critical in this manner. It's really important. And probably choose something with a really small scope that's lightweight and non-critical to try with this approach first. So that leads us on to the next point about restructuring existing projects. So it's taken us some time, even though we defined the approach, the theory is really nice, everyone agrees with it. It takes some time to make sure the micro front ends are actually integrated and replacing that functionality that we're trying to replace. So yeah, again, do this progressively, try and choose something simple first so you can really prove the value and demonstrate the concept to everybody, and prove that it's worth doing. The next point, so Nicola touched on this, is something where I'd say we haven't got to where we want to be yet. So it's a work in progress, but is around restructuring teams to fit this model. So we had obviously come from that model where we had what we refer to as pods, the teams working on big monolithic front ends, accidentally duplicating pieces of code between them. And that requires some carve out, so into what Nicola, I think, referred to as enabler teams and product teams. So where the enabler team is working on the smaller components that could be shared, and the product team is more of an integration team, and then working on some of the business or domain specific code. This, yeah, as with any team restructure, takes time, needs to be thought out, and it's one of the challenges and something that's ongoing for us. And then the final one, which is probably the biggest challenge for us, and one where you need to, throughout this whole journey, keep your QA team, or whoever the people are who are helping you with those documentation processes, the administrative processes, they need to understand what it is that you're doing. So make sure that you've shared the concept with them. Make sure you take the time to explain fully what it is that you're trying to achieve, how it's going to streamline the process, and fundamentally make sure that once you've implemented the micro front end, that you're also removing some administration and documentation from other parts of the process. So you're not just adding a new technology, you have to remove some of the overhead at the same time. And so that's really working so closely with the QA team it's a fundamental thing. A quick reminder, just to finish, of some of the guiding principles that we touched on. So remember the mission. So the mission for us was to reduce the administrative overhead, increase agility for regulated app development and deployment. So help us to move faster. So some of those principles. So the micro front end is an independent application, and it has to be treated in that way in terms of your technical processes, but more importantly for us, in terms of your administrative processes. So smaller releases with a smaller scope and documentation covering that scope, not the scope of an entire monolithic application. Communication, so this is referring back to the loose coupling communication between apps. So event communication works really well for us, but you must have strict validation, which we are, like we said, are not where we want to be yet. And most importantly, keep it simple. So try not to have, or let's say, avoid tight integration between each part of the app, because it will just become overly complex. You'll introduce tight coupling, and in many cases, it's probably not necessary. Dependency sharing is really nice, nice feature to reduce the size of your download, but make sure that you have a clear testing strategy so that you can prove to an auditor or justify to your QA team that we can have these shared dependencies, because we know, thanks to our automated testing strategy, that we're not going to break anything. And final point, as with the previous slide, is about the team. So really follow that microservice principle, actually, of having a team for your microservice, have a team for your micro front-end app. Don't try to have, or at least this didn't work for us, don't try to have bigger product teams working on the product and then also working on some independent micro front ends. Really try and carve out those. For us, it's these two concepts. Probably will be organization dependent, but think through the team, take the time to think about how you want to change things, and also you can experiment over time. You probably won't get that structure right the first time. And with that, just a couple of links to share. So first one is the GitHub repo that for the code Nicola shared, and the second one is a link to the Single Spell website. And thank you very much, and we have some time for questions if you have any.
Go ahead.
Yeah, I was wondering if you have sort of this component that you load a second component. Do you have a way for those two components to interact? So you sort of load this component instead of another. It sort of have an implication on the first component, or do you keep the concerns completely separate?
We try to keep the concerns as separate as possible, because this way, if you just tie the communication across, so one component triggers another, you could easily create a logic that you don't want to have at this moment. So you would tightly couple things, you would expose the knowledge of a root application to the subset of applications that compose it. So we find it as an anti-pattern in this sense, if I understood the question correctly.
You understood correctly.
Yeah.
Yes.
Go ahead.
If I understand that if you have one product with multiple micro apps, a badly behaved micro app could, in theory, mess with the whole DOM, right? It's all in one package. So do you actually avoid the need to regression test the product when you release a micro app? It seems like from the regulated environment, there's still the risk that you could blow up the entire product when one enablement team releases this stuff. So do you assume that your CI/CD and the practices prevent that, and then it still allows you to do these independent pieces, or is it something else?
Do you want to take it? Or?
You hit the nail on the head with the CI/CD processes. So yeah, the critical thing is making sure that you do have some, let's say, I don't know, integration or end-to-end tests which are in place, which allow you to make sure you're not going to release something which is going to crash everything. But the point is that those are executed automatically, but they're not considered as a change to the parent or that integrating app. So it's more in releasing my micro app, I will automatically trigger this test suite. But I'm not going to have to go through all of the administrative overhead of doing two separate releases or two separate test suite executions.
The test suite includes products that use that app.
Yeah. Is that?
Yep.
Yeah.
Major updates of the shared dependencies, and let's say that one micro front end is used in several applications, and now one application wants for some reason to upgrade. I mean, it depends.
You mean like Vue? You would, okay. So
Micro changes, and all of a sudden you see you find yourself having to upgrade every app using a certain micro front end. One app wants to.
So for this, we have a pattern that we use. So in majority of cases, we have a standardized things. So we have a certain version of Vue that we use for us. But in reality, how it works, majority of your applications, at least for us, are running on the same version. So we keep this one as a shared dependency. And of course, it's possible that one of your products is going to evolve. In example, this whole repo is written with Vue 2. Maybe somebody wants to use a composition API and switch to Vue 3. You can do that. You just don't configure your Webpack to take the shared dependency. It rather uses the view from below. It can even use React. So like I said, in this example, we just stick with Vue, but you can have as many dependencies. They can be shared or they don't have to be. We just follow the practice that we share the dependency that's used by majority of the applications that we have. So if at one point Vue 3 becomes the dominant one, only then we would update the root configuration that we share the dependency of Vue 3. Until this happens, we share the Vue 2.
And then you will have to
Well, with a specific micro frontend, yes, yes. Unfortunately, it's unavoidable. But the same can be said that you load also React and Vue and Angular at some point. So it's simply unavoidable, and this is exactly why we want to use this one.
The shared dependencies automatically understood by the single spa, or do you have to manually include it in the root?
So in the root config, you need to import the ones that you want to use. So this is the one that's going to declare for every micro frontend or every parcel that you want to use there. You need to define it. But on the level of the application, you need to configure, or each micro frontend, you need to configure a Webpack. Do you want to use this shared dependency, or if you want to use the one that you have?
In terms of team structure, find which team is responsible for the root content itself, because this is critical.
Well, in reality, once you start building micro frontends, you need to have root config per each project. So you need to have, for each of these applications, if you want to independently deploy it, you need to have a root config that's going to deploy it. So everybody's responsible for the one that their application uses. So maybe you're going to have multiple applications, and you will be responsible for that one.
So that the integrating app is the one that's going to manage the root config, and that will say, okay, I need to import micro front end X, Y, and Z, and that they will manage that root config.
Exactly. Go ahead.
I was wondering what's been most difficult for you to this project?
Sure. Let's see if we both have the same answer. For me, we talked about learning curve and things, but for us, it's the problem we're trying to focus on and highlight in this presentation for us is how do we streamline the process, and it's making sure that people really understand the concept and accept that if we implement this, the deal is that you help us to streamline the process behind it. And so that's always, within Sanofi, we have really very good relationships between dev and QA teams, but it always takes time for people to understand the concept and figure out, okay, that means we can take this approach in the documentation or this approach in the release. So that for me is probably the biggest challenge of getting that message through and getting it widespread and understood and accepted enough to be taken on board.
Maybe to rephrase this, it's always easier to explain this concept to technical personnel working on implementing this rather than quality personnel that doesn't have a technical background in this sense. So this was the most difficult part, to change the processes within and make it widespread. So we're running also some internal presentations trying to educate people on how this can help us accelerate our development processes.
Save the money.
Save the money. Be the leader.
We missed that one, and it's probably going in the next slide. I think we've run out of time. I want to say thank you so much to everyone for coming. We hope you took something from the presentation. So thanks a lot, guys.
Thank you, everybody.
Morning. Morning. Is that on? Yes, you can hear me? Cool. Talk amongst yourselves for a moment. Okay. Is this thing working? Hello. Okay, first off, is anyone from Lego here? Oh. That's good. Okay, thanks very much for coming. First of all, good morning, everyone. Have you had a good conference so far? Yes, good. Okay, so much like yesterday, I talked about my journey, I guess, in terms of software architecture and things. This is about another side of what I've learned over the last, whatever it is, 27 years or so, which is about how to deliver software most effectively, I think, or more effectively, or how to deliver work, in fact, more effectively. I first did this talk 10 or so years ago. And the reason I put it together is because we did some work for Lego. So I worked for ThoughtWorks, and we were asked to help Lego out a long time ago with a massively multiplayer online game that they were building. I think it was the precursor to Universe, if you remember that. And the reason we were asked to help out is quite simple. Essentially, the game was, there's an open world which you would wander around in, much like the single-player Lego games. If you played those, you do stuff, collect bricks, and then in your sandbox, you could build cool structures, and then you could publish them, and all your friends could see them and play with them as well as you, right? In the open world. So sandbox, you build stuff, publish to the open world. Now, the problem is, if you're a child, or if you're specifically a little boy between ages, there's one thing that you try and build first out of Lego in your sandbox. And they're things that you probably don't want all the other children seeing, right? Essentially, there was lots of genitalia being built in this game, right? So we were asked to help with performance tuning of the detector for these structures. This is true. This is actually true. I'm not joking. So I had two of my colleagues. They went to Billund. Have you been to Legoland? People been to Legoland? Anyone stayed in the hotel? A couple of people stayed in the hotel. I've stayed in the hotel in Windsor in the Legoland UK. It's great. We go every year, actually, me and my son. It's not somewhere where you would normally put up two consultants, shall we say. It's basically a hotel made of Lego, and you come down for breakfast, and it's unlimited ice cream. Amazing. But, not when you're on your way to a day's work. The sugar rush kind of kills you. So about 10 years ago, as I say, we did this work. And as a thank you, at the end of the engagement, our clients in Lego, they took my colleagues to the store in Legoland. They said, is there anything here you sort of like the look of? And it's like, people in a candy shop, right? For men of a certain age, or people of a certain age. So they saw this thing, the Millennium Falcon. The Millennium Falcon, the Ultimate Edition, had just come out, the first release of it. At the time, this was the largest Lego set that had ever been made. And they said, we quite like the look of that. And about 3 weeks later, in the London office for ThoughtWorks, turned up the Ultimate Edition Millennium Falcon, along with a model of the London Bridge as well. I'm not talking about that. So this is the story, essentially, of how me and a few colleagues, over the course of a Christmas holidays, if you like, put the Lego Millennium Falcon together. It's not just that. I'm going to try and illustrate a series of points around lean software development or lean product management or lean product development as part of it. So hopefully you'll get something else apart from the story of building the Millennium Falcon. So this is the agenda. This is what I'm going to talk about today. I'm going to talk about, I won't talk about ThoughtWorks because that's too salesy, so forget that. I'll talk a bit about Lego. I'll talk a bit about Star Wars, and I'll talk a bit about flow, lean product development. So do a recap on Lego. Does anyone in the room not know what Lego is? That's my recap on Lego. Fine, good. It's pretty easy, that bit. We should probably do a recap on Star Wars. has anyone not seen Star Wars? And there is always one. There is one. There you go. So, okay, you might want to go la, la, la. Unless you've deliberately avoided the whole thing, right? You might want to go la, 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 because there's spoilers in this. Incidentally, has Obi-Wan come out here yet? Oh, my God. Awesome. I was going to come on. If it has, I'm just standing there going, oh, hello there. So let's do a recap on Star Wars. Episodes 1 to 3, well, we don't talk about 1 to 3, right? So that's past history. We pretend they don't happen. We just forget about it entirely. Episode 4, well, this is the summary of the plot. Boy realizes he can do magic. It's pretty cool. Falls in love with a girl and sticks it to the evil empire. Now, did anyone notice the horrendous casualty figures in this? Tens of thousands of innocent stormtroopers died at the end of this movie. Well, that's pretty... How can they be the good guys? Episode 5, boy's mate gets frozen. Boo. Boy learns how to do magic. He finds out his dad runs the evil empire. That kind of sucks. Episode 6, boy understands he loves the girl as a sister, which is quite lucky. Phew. Boy fights dad, dad fights boy beats dad, etc., etc. Party. Ewoks. Episode 7, girl realizes she can do magic now. You can see where this is going. Falls in love with a boy, sticks it to the evil empire. Something bad happens to one of the dudes. The boy's back, except he's old and grumpy. My God, Leia! No, not Leia. That's the main spoiler. And episode 9. What? Like there was a guy. He was in the first. He was dead. Yeah, I'm all the Jedi. That's all you need to know about Star Wars. That's pretty much the entire plot of the 9 movies so far. Is that all clear? We've all got that. You agree with it, right? Yeah, that's fine. Okay, good. Okay, I'll do a brief recap on flow. So this is what I mean when I say flow. Flow of stuff, flow of work. I think it's the idea of system optimization, optimizing the entire thing, the system that you're working to keep stuff moving as fast as possible. I think I quoted Dan North yesterday when he sort of said, working to safely and sustainably reduce the lead time to thank you. That's what we're looking to do when we're looking to optimize flow. That's my definition. I will briefly introduce myself. This is me, clearly. I've been doing some writing recently on patterns of legacy displacement, so with 2 of my colleagues. So I'm sure people have come across the strangler vine pattern before. Now, if we talk about replacing legacy software or displacing legacy software, everyone always says, oh, we'll use the strangler vine pattern. Everyone nods sagely, yes, we will use the strangler vine pattern. And then, what the hell does that mean behind the kind of hand? Because there's actually quite a lot of stuff that you really need to kind of understand if you're looking to displace legacy systems. What does the strangler vine actually mean? What are the sort of technical and business patterns, analysis patterns and techniques you need in order to successfully migrate away from a mainframe or from a big monolith or from whatever it is? So trying to deconstruct things like the strangler vine and create a pattern language and a pattern library that we can use to communicate about displacing legacy. I'm also a massive nerd, in case you haven't guessed. This is me with my 13-year-old son at Warhammer World in Nottingham. We both like painting Warhammer 40,000 figures. And there's a lot of us about. Now, witness the firepower of this fully operational conference talk. Well, it's not a galaxy, it's an office, and I wish I'd licensed the music, so I'm sorry, it would be much more dramatic, but I don't have the music. A long time ago, in an office far, far away, lean Lego. Episode 4. Remember, we don't talk about episodes 1 to 3, right? Episode 4, a new box. So this is what the box looked like when it turned up in our office. You can see a few things about this box. The first is 16 and over. If you've spent much time building Lego, you know that they have age ranges. This is for people like me, adult friends of Lego. There's a name for us. That's quite sad. I have a lot of this at home. I was just talking with Lars outside. I can't see if Lars is in here, but just talking about the fact I've got the Apocalypseburg set from the Lego movie, and I've got the big pirate ship, I've got the Ghostbusters fire station, and all sorts of cool stuff. But anyway, this is the Millennium Falcon set, the original Ultimate Edition, Ultimate Collector's Edition Millennium Falcon. Another few things you should know about this box. It's a 300 double-sided page manual. There's quite a lot of instructions in this. This is what this looks like. And about over 5,000 pieces. At the time, it was the biggest Lego set that they'd ever made. This is the team. This is my friends who got together. So we were in ThoughtWorks, because we're hippies, right? We call it being on the beach rather than on the bench in many other consultancies. So we were on the beach, like, enjoying ourselves in the London office before Christmas, and we thought we'll get together and we'll build this thing. I did promise it's not just about Lego and Star Wars. There's a bit about like what we do, how we do it, and how we can use some techniques and tools to make the way we do stuff better. So I'm going to introduce a few of these now, and I'll be using them to illustrate progress over the course of the rest of the talk. So I appreciate you will know some of these tools. You will have seen some of them, used some of them, probably use them on a day-to-day basis. But I like introducing them because it calls attention to the fact that they're there for a reason. We use these tools for a reason, not just because we have to use the tool. And what do I mean by that? Well, I'm sure lots of people in this room, when you're building software, you might use a story wall, right? Or a Kanban board. Maybe it's in Jira these days. Maybe it's physical, like in the before times, like this. Who uses a story wall in the room? No, everyone, not everyone. No, actually not everyone. Most people just can't be bothered to put your hands up, right? Fair enough. I've got your numbers now. I'm watching you. So this is a story wall. So why do we use story walls? Why do we visualize work? Well, as I said yesterday, the reason it's important for us to visualize work with what we do is because the work we do is invisible, right? It's in people's heads. It's in the person who comes up with a requirements head that turns then into something that is maybe on in a Word document, a business requirement document, gets elucidated into requirements, which gets turned into something that we can work on. The reason we use these is if we didn't use these, that work would be invisible. We wouldn't be able to see the stuff that was coming up. And as I said, if you're in manufacturing, it's a very different thing, right? It's a very different process that you go through, very different idea around managing inventory. Because if you're in manufacturing, you can see when stuff, or retail, you can see when you've got too much of a thing or too little of a thing, because you can look at it. Is there anything there? No. Well, we've got too little of the thing, right? Is there loads of stuff there? Then we've got too much of a thing. You can see when parts of your process are broken, right? Because you can look and see where stuff is building up, where you've got inventory building up, ready to be turned into widgets or something, right? We can't see that unless we visualize it. This is probably the biggest, I think, win from agile software development over the years, is visualization, visualizing work in progress, visualizing inventory, visualizing the amount of stuff that's in our system of work. Because what we can do then, using other tools, is understand where blockages are, where constraints in our processes are, understand where the system is broken down, and work to optimize it. So in these story walls, we tend to have swim lanes. We'll have, the simplest one is to do, doing, done. But you might have, ready for analysis, in analysis, ready for dev, in dev, ready for QA, in QA, ready for deployment, deployed, as a series of process stages that work flows through, in the same way that an orange flows through a series of process stages from Seville to my table. It just involves trucks and it involves warehouses and so on. But the same thing happens, physical stuff moving through a process. And I'll come on to the importance of these ready for stages a bit later. But the key thing to note is we have not just in dev, but we have ready for dev. We visualize queues in our system. So this is a build-up chart. ThoughtWorks, we try not to use things just because a process document says so. So we don't burn down like Scrum does, or generally used to. We burn up to total scope. So we understand how much work we've got to do, and then on a week-by-week basis, we burn up via velocity or counting the number of stories delivered, whichever is appropriate. As this is a burn-up chart. Now this is where it starts to get a little bit more esoteric. Not everyone in the room, well, generally not everyone has come across cumulative flow diagrams, or finger diagrams, finger charts they're called. Anyone use these daily? That's a zero uptake on that. So the thing with cumulative flow diagrams, it's essentially taking your burn-up chart, or burn down, but burn-up chart, and plotting not just the total number of points completed, but the total number of stuff done per stage on your board. So what we're seeing here is each of the colored areas represents a swim lane in the storyboard, if you like. And what this allows you to do when you use these is to identify constraints in the process. So you can see, for example, we've got this pink thing down the bottom here, this pink area, which represents the amount of work that's been showcased. So at some point here, we had a showcase, and then loads of work was fine, signed off by our PO, but then there was no showcases for ages and ages and ages and ages and ages. And loads of work was building up and building up and building up until we finally had a showcase again and these deployed stuff. So you can start to identify blockages, constraints in your process using these. Value stream mapping. There was a talk yesterday. Unfortunately, I was a bit exhausted and sort of adrenaline filled after my opening talk. I missed the talk on flow engineering. But I know they talked a lot about this because I sort of glimpsed it through the window. A value stream map, very simply, is where you track the activities within the process and how much time on average they take to perform. You get two different types of activity. In this case, you've got value-adding activities, which are the top bits, 3 days, 1.5 days, and a half day. So you can imagine this is 3 days of development work. This is actually from a client, 1.5 days of testing, and then half a day of deployment. Value-adding activity, taking the thing, turning it into something that's more valuable via writing code, writing tests, and deploying it. And then the sort of the bits that are kind of like the down steps, as it were. There's probably a name for that in maths. Where you've got 2 days, 10 days, and 30 days. These are wait times, so times waiting between value-adding activities. So even though you've got 3, 4.5, 5 days of stuff that's adding value here, 5 days of adding value, how long are you waiting? You've got 2, 10, 30, 42 days of work just sitting there not doing anything. What's the problem with that? Well, because that stuff, that requirement could be in could be in production making you money. There's a concept from lean product engineering called the cost of delay. Now, I like this idea of the cost of delay. The cost of delay is, I kind of think of it as like a game show. When someone doesn't win the prize on the game show, and they're like, oh, poor you look at what you could have won. And it's like a boat or a car, but you didn't win it, right? So you're like, oh, God, didn't win it. The cost of delay is the same thing. It's how much money you could have made if you'd got the thing into production earlier. Now, if you reduce some of these times on here, reduce the 30 days between testing and deployment to 1 day, then you've got 30 times more money you could have made out of that one particular requirement. So value stream maps are really, really important, a really useful way of identifying what's going on in your system, identifying where your constraints are, where your blockages are, and where you can reduce waste, essentially. And generally, just by plotting these things out, we're all smart people. When you take a look at something like that, your first reaction is like, why does it take 30 days to go from here to here, right? What happens if we shrink that? Can we deploy to production every 10 days, every week, every 5 days? Can we do it every 1 day, say? And often, just by analyzing the wait times in your processes using value stream maps, you can improve throughput, you can improve the amount of work you get through into production by orders of magnitude without doing anything else, just by trying to work on wait times. This is another rather more esoteric one. So this is a control chart. So instead of plotting number of stories cumulatively or velocity cumulatively like in a burn-up chart, this is where you plot basically velocity and work out what the average velocity is over time. So there's a fact within systems engineering, as in control systems and things, right? From manufacturing, where essentially you don't look at individual process steps. You look at the system as a whole over a period of time, because every system has an inbuilt variability. Every system, even machines, are variable. Sometimes they'll take 1 minute to produce a thing. Sometimes it might be 1 minute, 10 seconds, sometimes 90 seconds. So by tracking the variability of your process steps, you can understand what's normal. Right, so how many of you have been in that situation where you've been, plodding along, doing quite nicely, you've done, a number of story points, and then the next week you do, there's a really gnarly requirement, really gnarly user story, and it doesn't quite get done by the end of the sprint. and it follows on to the next sprint. And so suddenly you're doing way, way less user story points, maybe half. And your manager goes, why have you done? Well, you should be working harder or something, you know. But actually, if you start plotting these things on control charts, what you understand is over time, that's just what the system looks like. You're going to have a natural variability of how much work you get done every week. And then the important thing is these upper and lower control limits. These are 3 standard deviations either side of the mean, right? So you can plot this, and then when you have exceptions outside the control limits, you can then investigate. Why did we do 50 points this week when we only did 10 points last week? That's way outside our control limit. Or why did we do nothing this week when we did 10 last week? That's outside our control limit. But if it's between the control limits, that's just your system. There is no point. That's just how the team is working. Interestingly, this is where Six Sigma comes from, if you've come across that lean methodology. Six Sigma comes from control charts and 3 standard deviation sigmas either side of the mean production rate. Okay, fine. You're like, teaching your grandmother to suck eggs. No idea if that translates into Danish, but I'm teaching your grandmother to suck eggs in English. And we'll get back to actually the process of building the Millennium Falcon. And I promise you, this story actually happened. This story did happen. We didn't use all the tools at the time. I might have retrospectively cast what happened into the tools, but this did happen. So the Lego strikes back. So first of all, what happened is we all looked, 5 of us took a look at this set of instructions, and we're like, oh, this is really, really cool. Look at what's amazing, all these like knobbly bits and Lego Technic bits and stuff. And then we all jumped into the box and found all this stuff, and then we all put stuff together, right? We all just put the bits together. There's 5 of us all like, yay, super excited, more Coca-Cola, whatever it is you're drinking, more coffee. And the thing is, doing that went really, you're having fun, but it went really, really slowly. The amount of time it was taking for us to get anything done, it just took a long time. Everyone's searching for these things, everyone putting it together. It went really, really slowly. And it turns out this is what the value stream map for our system looked like. In fact, this is what the value stream map for the system of building Lego looks like, right? So you have a value-adding activity, which is finding bits, sourcing inventory, and then you have a value-adding activity, which is putting those bits together. So you have finding pieces and you have assembling pieces. And it was taking ages. And that's my first tip, right? Use these tools. They're there for a reason. They're not just kind of, there for consultants to kind of show you shiny pictures. They're actually super useful for understanding the system in which you work. Understanding where your value-adding activities are and where the wait times are in between those value-adding activities. So understand the system you're working in. And what was happening is we were processing our work serially, essentially. Everyone was finding stuff, and then everyone was putting stuff together. So there's 5 of us finding stuff, 5 of us assembling stuff, 5 of us finding stuff, 5 of us assembling stuff. Woo, it's exciting. Look at all this Lego, it's amazing. That's the second tip, right? You use these Kanban boards and story walls to visualize your system. Right? They're there for a reason. It's not just so you can have a nice shiny Jira wall that you can show your management team, right? The reason we have these things is so as a team we can understand and analyze how work is getting done, how flow is happening, how requirements are flowing through from idea through into thank you. So use these things to visualize your system, to make the work visible. So what was the result of this? Well, the result of this, well, it was going slowly, as I said. And in fact, we worked out using a burn-up chart that we were going to take until the heat death of the universe to put this thing together. Now, we're in professional services. We, us meatbags or invariant terminating units or whatever you want to call us, we tend to have to bill, right? That's what our job is. We're on client site building software for people. And asking for 5 of us to wait until the heat death of the universe in order to build the Millennium Falcon was probably not gonna fly with our leadership team. You can tell how old this is. It's pre-meme, but it is after emoticons, which is good. So boo. Episode 6. The return of the process Jedis. So a funny thing happened. This is our system of work, right? These are the value-adding activities, finding pieces and assembling pieces. And so, as I sort of said, we started off with everyone doing one thing and then everyone doing the following thing. So everyone finding stuff and everyone assembling stuff, you know, in sort of serial. We started doing something else. We started to specialize. We started to have some people finding bits in advance of some people putting stuff together. So, and they were doing this at the same time, just one in advance of the other, much like, you know, BAs are working on user stories or doing analysis in advance of developers picking up a piece of work, or developers finish a piece of work before QAs are doing exploratory testing. We had different people at different stages of the process. See, there you go, that's us doing it. We had some people looking for stuff, some people putting stuff together. So what we did essentially was identify a constraint. By understanding where we were going slowly and why we were going slowly, we identified a constraint in the system of work. I don't know if anyone in the room has come across the more modern version of the goal, but the Phoenix Project, which is a business parable about the theory of constraints and optimizing systems, essentially, which is based on an original version called the goal, which is about lean manufacturing by Eli Goldratt. And in the goal, Eli Goldratt identifies this called the theory of constraints. What the theory of constraints says is, in any system of work, originally manufacturing, there will always be a constraint. There will always be a constraint, a bottleneck that you can identify. All right? So what we should do in order to optimize our systems is to work to identify what the constraint is, identify the bottleneck. Then I think the exact phrase is subordinate everything else to the bottleneck. So if you've got a machine and the machine is the bottleneck, you basically make the machine go as fast as you possibly can. And then when the machine is going as fast as you possibly can, you can't really do much else, right? Because the machine is going as fast as you possibly can. You might add another machine, or that might be an option to do. But generally what happens is the machine is going as fast as you can, now move on to the next bottleneck, and then the next bottleneck. That's the theory of constraints. There's a great story from the goal around scouting, if anyone's read the goal. But Eli Goldratt uses the story of scouts going on a hike to illustrate this. So he says, you know, you've got a scout troop and you've got one member of, maybe there's 10 scouts, you've got one member of the scout troop who's a bit less fit than the others, but they've also rather stupidly packed like loads and loads of stuff. And everyone else is just carrying a bivy bag. This one scout has got, you know, kind of pots and pans jangling off them. They've got like, you know, loads of really heavy food and water and all sorts of stuff. And they're going really, really slowly. And so what happens is, you know, the scouts at the front are going faster, and there's this poor scout at the back who's getting further and further behind. That scout is the constraint. So how do you solve that problem? Well, there's a number of ways you can solve the problem. In the goal, Eli Goldratt says what you could do is you can identify that the fact that scout is the constraint. You can work to minimize the amount of weight that the person's carrying, right? So they might walk faster if they haven't got all these pots and pans. So you distribute all the pots and pans around with the other scouts. And then you try again, and they go a little bit faster, but they're still quite slow because they're quite unfit. The end result of the story is what you do is you put the unfit scout at the front, and then all the other scouts behind, and then you all walk at the same rate. The system operates at the rate of the lowest performing member, essentially. And that's the theory of constraints. And what we did in this is we identified this constraint. It was around, you know, these bottlenecks around finding people, finding things. And it turns out you can find pieces in parallel, right? It turns out there's lots of stages of the manual on each page. So some people could find pieces for one bit of the manual, and then some people could find pieces for the next stage of the manual, and some people could find pieces for the next stage of the manual. You could work on all these things independently from one another and build up this backlog for the people who are putting Lego together to work on. So use the theory of constraints. That's the next tip. Use the theory of constraints. So the next thing is this, I mentioned at the start, this idea of queuing theory. Queues. Queues are everywhere. Queues are the root of most evil in most processes, in fact. I said there's a great book yesterday called Principles of Product Development Flow by Don Reinhardtson. This blew my mind when I read this book. I read it, I reckon about 2009, maybe. Dan North, if you know Dan, so Daniel Tuhilst North now on Twitter, he recommended it to me and I read it. And I was like, oh, that's kind of interesting. It's very dense. It's like 280 odd principles to improve flow, right? To improve how work flows through systems. It's quite dense. I thought that's kind of okay. That's interesting. But then I read it 10 years later. I read it back in 2017 because I was going to Australia to a conference and Don was keynoting. I can say Don, I know him. I met him. It's cool. And he was keynoting, so I thought, God, I better read his book again. I read it on the plane on the way to Australia, and it literally blew my mind. I was like, why didn't I get what I got out of it like 10 years ago? And it's because I think the journey I'd been on over 10 years meant that I was able to take so much more from it. All the questions I'd sort of had about the difficulties of managing processes and teams, he seems to have answers to all of them in this book, right? And even better, he has economic answers to these things. Why should we do this particular thing? Why should we change the team shape? Why should we change our process? Why should we optimize for smaller batches and do continuous delivery? If you've ever had to convince someone to give you budget to improve your build pipelines so you can release software more quickly, Don has got the economic argument for why that will make you more money. And that's super, super interesting if you're trying to convince people who are interested in finance about why they should give you some money to do stuff. It blew my mind. And in this book, Don spends a lot of time talking about queues and queuing theory. So what do we learn in QS in Computer Science 101 about queues? Well, we need to manage queues quite carefully. What happens in a messaging system if queues start backing up, right? Queues start backing up, you've got lots of messages that are just sitting in a queue waiting to be processed by a consumer, maybe competing consumers. Well, what you can do is you can add more consumers into that process, right? I don't know if you remember from queuing theory, but what you have is the idea of a number of you have basically a number of processes or services that are processing messages coming in from a queue, and then they output a number of messages as well. That's basically, you have this, and the number of messages coming in versus the number of messages coming out is a measurable rate you can look at. But the problem is when you back up queues, when you get messages sitting at the bottom of a very big queue, well, obviously that message will take longer to process than if you've got a message at the top of a queue, right? So whenever you've got queues of stuff and the queues grow, what happens is essentially your cycle time increases. The lead time for the thing to be processed gets blown. So if you think about work, we've got a Kanban board. Has anyone got like one of those sort of defect boards which has got like 5,000 defects on it? Right, that's kind of classic enterprise kind of thing, where you've got 5,000 defects, and like you're never going to get through any of them, right? Even if you spent from now until the end of your career, you'd probably only put a dent in a little bit of them, because you're trying to process a massive queue and process a lot of work off a massive queue. Dan North has got a fun trick. When he turns up in consulting mode, he often just deletes all that. Because if they were important, they would have been done already, right? So just delete it all. Delete all that stuff you haven't done yet. But the funny thing that happened is that we started to create natural queues, essentially. There were natural queues as part of the manual. So the people finding bits started putting bits on the picture, and then they put bits on the next picture, they put bits on the next picture. So we started to build up like a ready for assembly queue. So we visualized this queue in the system, this idea of pieces that are ready to be assembled based on the pages in the manual. And then the folks assembling pieces, assembling the Lego, putting the Lego together, they started pulling from the queue. So we were finding bits, pushing into the queue, and then we were taking stuff from the queue. So this idea of visualization, which runs through this whole thing, visualizing work in progress, visualizing queues in particular, is kind of a key. Because when you can identify where the queues are, you identify how deep the queues are, how much stuff is in the queues, you can basically managing that, visualizing that helps in maximizing throughput. And I'll give you a quick example of that here. It's also a leading indicator, queue size, of how quickly you can get stuff done. So 4 key metrics. Lead time is one of the 4 key metrics. It's not a true lead time, but lead time as defined in the door of the state of DevOps reports and then Accelerate is from developer committing a line of code to that code earning money in production, right? It's the lead time to value for that piece of code. Right, so cycle time here, that's what we're talking about, lead time, cycle time. Again, it's quite funny. The reason I sort of say it's not really lead time is because lead time would be from when the requirement was defined all the way into production. Requirement defined all the way into production, not this little bit of it at the end. Because you can imagine being infinitely quick, infinitely fast. You could be an infinitely fast developer team that took 0 time at all to get code from commit into production. But if it took you 8 months to get the requirement to that point, like you've still got an 8-month wait before you make any money, right? So kind of that little bit of it is kind of interesting, but not the whole story. Anyway, the point is, if we want to minimize cycle time, we want to make stuff flow through our system more effectively, more quickly. And one of the ways we can do that is by looking at leading indicators for cycle time, and queue size is one of those leading indicators. And I'll illustrate this with an example from conferences that you might be familiar with. So say we go to lunch at 1 o'clock in the afternoon. It's lunchtime, I'm going to finish the talks, yay. There's been a bunch of people who haven't been in the talks, right? So there's going to be some people who are kind of just milling around, maybe in the expo area, maybe upstairs on the second floor, whatever it is, and they're going to kind of go to lunch, and then all of a sudden, the session's finished, and a ton of people go to lunch. This is basically your arrivals into your lunch system from conferences, right? So you've got an arrival state where you've got a sort of steady number of people just turning up, a ton of people suddenly turn up, and then you've got a bunch of, a steady state of people again turning up. This is departures. This is the capacity of the system to serve you lunch. It's a constant capacity, right? There's a constant amount of people who can be getting lunch at any one particular point. And it's slightly delayed from the people arriving. That's the amount of time it took them to serve lunch, but these are the departures from the lunch queue, as it were. So sessions finish, a ton of people arrive. Essentially, the length of time it's going to take you if you arrive at the queue here, right? The cycle time is this difference over here. So if you arrive halfway up this thing, it's going to take you bloody forever to get lunch, essentially. Whereas if you're down here and there's no queue in front of you, it's not going to take you very long at all to get lunch. Essentially, what we can do, because this vertical axis, this is queue depth. By measuring queue depth, how many people are queuing for lunch, not how long is it taking them to be served, we can work out cycle time. And by controlling queue depth, we can control cycle time in advance, which is super interesting. And actually, NDC normally, if you've been to Oslo or to the other conferences, what they normally do is do lunch continuously throughout the day. They have little stalls everywhere. So you go and you can just pick up some lunch at 10 o'clock in the morning if you want, or 3 in the afternoon. It's continuous lunch service, which fixes this problem. Because what you have, in fact, is the continuous arrivals and departures, minimizing cycle time. But this is the importance of queue size. And by visualizing queues, we can basically work out what our cycle time is and how to control cycle time and how to improve our cycle time. As a result of all this work that we did, we got faster. See? So now we're into a number of hours, how quickly we can put the Millennium Falcon together, which is good, because 48 hours, that's what, if we're doing 40 hours a week, just over a week's worth of work, that's good. We can actually get stuff done before Christmas. Excellent. That's my next tip. We can use burn-up charts, and as we see here, yesterday's weather to track progress. So what does yesterday's weather mean? You've probably come across this from Agile. It's, if you look at what's today's weather going to be like, well, 70% of the time, it'll be the same as yesterday's weather. So how much work are we going to get done this week as a team? 70% of the time, it's probably going to be about the same as we did last week. And you can use that to essentially estimate when you're going to get stuff done, roughly within orders of magnitude, 50% either side or something. So use burn-up charts in yesterday's weather to track progress. But we didn't stop there. Other funny things started happening. And I repeat, this did happen. All of this did happen. The team became T-shaped. Now, I'm sure you've come across this idea of T-shaping, right? Generalizing specialists. I'm very deep in Java, mainly Java. That was most of my career, but I've also done a bit of Scala, a bit of Clojure. I've done some C#, tiny bit of F#. didn't understand it. Wasn't that a joke from yesterday? But also distributed system design, software architecture. I can, at a push, pretend to be a business analyst, right? At a push. I can pretend to be a QA for a couple of weeks, then I'll get found out. But my depth is in, is in Java, is in software architecture, and the technical side of what we do, more technical side of what we do. And that's what we mean by T-shaping. We want people who can act in different roles according to need, right? That's a way of optimizing our process again, optimizing our system. So what we ended up with is a couple of people who were specialists in putting the Lego together, and a couple of people who are specialists in finding the bits of Lego. And it probably is kind of obvious why, right? And if you're putting stuff together, it's a big, complicated, topological puzzle, essentially, building this thing. And it's quite hard sometimes. It says 16 plus on the box. It's quite hard to actually understand how the bits go together. But the more you do it, the easier it is, I kind of see where this is going. I can put this bit there and then this bit there and that there. Similarly, if you're looking for stuff and you've got some little bit to find, I just saw that a minute ago. I'll just go and get it. You get quicker, you get more effective in your role as you specialize. But it didn't mean that the people who are finding things weren't able to put the Lego together, right? They could still put the Lego together as well. And the people who were putting the Lego together could still find things. And those specialists noted this. This is a control chart. This is the amount of time it took to find pieces. What you can see here is tremendous amount of variability in this process, right? Sometimes it's taking 0 time at all, or hardly any time. Oh, there it is. Sometimes it's taking loads of time. What the hell is that little thing? Lots of variability. It turns out that when you've got a big set like that and all the bits are in one place, finding a piece is a function of piece size and the total number of types of pieces that there are. So if you've got a big thing like that, it's a lot quicker to find, and you've got lots of them, than if you've got one tiny thing out of 5,000. Right? So it's inherently variable. So how do you fix that? We started just in time grouping like bits of pieces together. We started creating little sort of inventories, sub-inventories, if you like, grouping little bits so that we could go and immediately find stuff. But what we didn't do is do it all up front. It happened sort of just in time as part of the process. And that meant that the variability massively reduced. Right? The variability of the system, we identified that there was variability in the system, and how can we fix the fact that it's taken ages to do this? Well, what happens if we just put these little bits in little plastic cups? We got a lot faster again. So that's the next thing, this idea of control charts, understanding variability, understanding what your normal system looks like, what the normal variability of your system is, and working around exceptions, identifying when there's been an exception, working to understand why. Why did that story get blocked for 3 weeks? So we tanked on our progress. Or why did we go so fast this week? What was it about this particular set of requirements that enabled us to go so quickly? And then working to understand the variability and reducing the variability. There were other fun things happening too. This is a real defect card that we had from the project, I say. We actually did bug tracking. We had different types of bugs as well, 2 different types of bugs. We had cosmetic bugs, and we had proper defects, if you like, so P1s, or stop the line, broken build bugs. You can kind of see, if you've got something that's like just going to make something look a bit shinier, then you can defer. We'll raise a bug, can't find the piece. We'll raise the bug, stick it in our bug tracking tool, which is the table next to us. And then, when we find the piece, that's fine, we'll just stick it on. But sometimes there was a structural element that we couldn't find. At that point, red build, everyone needs to swarm to break the build, to fix the build, right? Pull the and-on cord from Lean. Right, the whole team needs to find this bug. So there you go, non-critical. This was a cosmetic type of bug. We also had work-in-progress limits, natural work-in-progress limits. We limited the amount of work that was ready to be done. The ideal with Lean product development is this, or in any Lean process, is the idea of single-piece flow. Right, so a customer asks for a requirement, and that requirement flows as a single piece all the way through into the customer's hands. This is the famous piece from the Toyota production system. Where, ideally, if I order a Toyota car online, that one order triggers all the processes behind it that lead that particular car to be built just for me. Single piece flow throughout the entire system. And the way you manage single piece flow, or one of the ways to help with single piece flow, is by limiting the amount of work the amount of work in your queues. So limiting queue depth, having work in progress limits. And there's another way in a minute. But can you spot how we limited the natural way to limit the amount of pieces that had been found ready to be assembled? We've got someone in the front.
Probably by
Yeah, by the pages in the manual, because you could only put so many pieces on it before you had to turn the page, which flipped all the Lego all over the floor. So we had this natural, like, work in progress limit based on the queued steps of pieces that had been found and placed on the manual. And the other thing we did is swarming. So because we have T-shaped people, we can both find stuff and assemble stuff. If we were blocked, because that we can't turn the page, we've found all the stuff we need to find, then those people finding things can help put stuff together. But the key thing is you swarm upstream. If you're a developer in a development process, you help the QAs out. Ideally, if you're a BA, you swarm and help the developers out. You swarm upstream to improve overall throughput, optimize the system, not just your little part of the system. Somebody sits there, well, I haven't got any work to do now. As much as that might be, nice. Sometimes that's nice for a break, but often you might be able to go and help the QAs who are like, oh my God, there's so much to do. And you can pretend to be a QA for a bit, right? So tip 7, limit work in progress and then pull more work from upstream. So you help the people out upstream of you. You help getting work through the process into production, stopping the blockages. Because the reason you have blocked work in progress is because there's a blockage upstream that you can't start. So here we go. We actually finished it in about 24 hours, this thing. And then the memes started, so you can tell where the new talk starts. Chewie, we're home. Rah! There's the Millennium Falcon, or the old one. There is a new one. The new one is so big, it comes in a box with wheels, and that's true. It nods, yeah. Yeah, so big you needed like a trolley thing. It's pretty astonishing. And unicorns. So where are we so far? My conclusion so far from the tips and so on. Understand your system. So use the tools available because they're there for a reason. They're not just because, it's not just a cargo culting process or mechanism we go through to get stuff done. These tools are there because they help us improve visibility. They help us understand where queues are in the system. They help us to understand where we can use the theory of constraints to identify bottlenecks and unblock them and so on. Right? So use the tools. Visualize work, right? Make stuff visible. Make the invisible stuff visible. Work to continually identify constraints. Use the theory of constraints. These ideas of things like queues, whip limits, swarming, they help keep they help keep throughput high. So what do I mean by that? Well, these things, they help us get towards the goal, the ultimate goal of single piece flow. One thing moving all the way through, unimpeded from idea or customer want through into customer thank you. And then use these other visualizations tools to understand when you're going to be done, when you're going to finish. Of course, if you're in product development, you're never going to finish, are you? But there we are. And then use control charts to identify and reduce variability in the system. So that's where I sort of stopped about, wherever it was, 8, 10, 9 years ago. That's where Lego was, that sort of time ago. Then I was asked to do a keynote for our ThoughtWorks conference, XConf, which is a really fun conference, actually, about 3 years ago, I think. And I thought I'd do a redux on this because, I've learned a lot since then. I've learned a lot about how to manage work and the importance of things like queues and so on. Lots of stuff has happened in the industry, right? Microservices has happened, for example. All these kind of interesting ideas around decoupling and how you can, scale more people around problems and so on. So what would Lego have learned in that period of time? Episode 7, 8, 9. They're like 4, 5, and 6, but just, a few years older or newer. Hi. So this is the only time I was able to go and expense a Lego set, which I did. It was great. I went and I bought a Nexo Knights, because my kids were loving Nexo Knights at the time. I bought this Nexo Knights set. You can tell this isn't as complicated. This is only 9 to 14. I should have got a bigger one, but you can't push your luck too much, can you? So I got this Lego set. And I thought, what would Lego do? So I'll ask the question. If you, 10 years down the line, if you were Lego and you were also constantly learning from the experience of building Lego, what would you do? What would be the change, the biggest change that you could make to have the biggest impact on the Lego system of work? And I've got someone with a yellow t-shirt with a hand up. Yes, please. Bags with numbers. And there's an interesting reason, a scientific reason why that works. So remember I said at the start, we've got all, basically the old Lego sets used to have all the pieces in one big bag, essentially. They were grouped into maybe sub-bits, but more or less just all the bits in a box. Taking ages to find stuff. You have to group stuff together. You're having to create these little bits of inventory as we go to improve our, to decrease variability and improve throughput. Well, this is from the principles of product development flow. The batch size queuing principle, reducing batch size reduces cycle time. Right. The single most important thing you can do when optimizing a process in terms of improving throughput is to reduce the batch size, is to reduce the number of requirements being pushed through into production, right? For example, that's what we mean by batch size. When we talk about continuous delivery, right, and continuous deployment, what we mean is, really, we're going to work to reduce the batch size to 1. So we can push a button, 1 requirement goes into production. As opposed to waterfall, where your batch size is maybe 100%, right? Your batch size is all the requirements which move as one batch through your process. And then all of them get tested, all of them get put into production. Continuous delivery is about reducing batch size. That's why it's so successful. That's why it works. And again, in another graph here, so batch size, queue depth, and cycle time, there's a relationship. Essentially, if we look here, this is time, as you can see. This is the number of stuff getting done, right? So if you've got a batch size which is 50% of the stuff, it's going to take that amount of time to start earning money on a requirement. But just by reducing batch size, you can get stuff into production, get stuff earning money way, 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 way faster. Average queue size proportional, blah, blah, blah. Little's formula, it's maths from queuing theory, actually, one of the most famous formulas from queuing theory. Don Runnison goes on to say, batch size reduction can enable us to shorten cycle time, often by an order of magnitude or more, without changing capacity or utilization. You can improve your cycle time by an order of magnitude without adding people or without having them work faster or harder. That's pretty cool. And that's the root of continuous delivery, right? That's what we should be optimizing for reducing batch size. I mentioned this book a number of times, but he talks about the effective queues here. This is essentially, queues represent batches. And queues create longer cycle times, increased risk, blah, 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 blah. Essentially, queues, big, deep queues, lots of stuff waiting for something to happen to them, big batches of stuff sitting doing nothing equals bad. If you take nothing away from this talk, take that. Here come the bags. So what Lego did was reduce the batch size. They basically, they say, okay, for the first 10 pages of the manual, you'll use bag 1. It's a smaller batch. For the next 10 pages, use bag 2. So it means you're reducing the variability. It takes much, much quicker time to find stuff. You can build stuff much, much, much faster. There's another thing they did as well. This is another principle from Don's book, the fluidity principle. Loose coupling between product subsystems enables small batches. You can build bits independently from one another. You can have multiple people building entire subsystems of these Lego sets, and then you can plug them together at the end. Does that remind you of anything from what we do? Pretty much the movement towards cohesive services around business concerns, right, that communicate via uniform interfaces. That's the fluidity principle in action for software architecture. And there's the finished thing. So my final set of conclusions is, first thing is understand the system, visualize it, use all the tools I've talked about already. Visualize cues. This is what I've learned, is that cues are the most important thing to understand. Where are the cues? How deep are the cues? How long does it take something to get from the bottom of a cue to the top of a cue? Identify constraints in your system. Use the theory of constraints. But you have to recognize its limitations in product development. I mentioned earlier the scout idea, right? How do you optimize for getting the scout troop to the end of their hike altogether? Well, in the theory of constraints, they're talking about manufacturing processes. He's talking about machines. He's talking about optimizing machines. Machines can only do one thing. As we've sort of seen, we can do more than one thing. We can be generalizing specialists. We can adapt. We can turn our hands to other things. We are human beings, not machines. Sounds like a bit of a call to arms, doesn't it? We are human beings, not machines. So another example in Principles of Product Development Flow, he says, instead of the scouts all walking behind the slowest and getting it at the same time, why don't you send some of the older, faster scouts on ahead? They can build a campfire, right? They could chop some wood. They could do useful value-adding activity whilst the rest of the troop catches up. We can do other stuff. We can swarm. Using work in progress limits and swarming helps keep throughput high. Small batches directly impact cycle time. And this idea of anti-fragility, building components, building smaller things that can integrate together, smaller, cohesive, decoupled components that can integrate together. So these are the sources from this. As I say, this did happen. Generally, that process of building the Lego set did actually happen, and we did go through all those optimizations. I've used the tools and the visualizations as a mechanism to describe and explain some of the ideas behind what we do in product development, what we do as software developers, and how we can use some of these ideas to optimize our processes. So finally, software should be cheap to replace, quick to scale, resilient, and it should allow us to go as fast as possible. The processes that we build to build software should allow us to optimize for flow and go as fast as possible. So the question is, what would Lego do? That's what you need to ask yourself. And Lego, they would use small batches. Control batch size, that's the key. Thanks very much. Enjoy the rest of your day. Cool. I'll be around. If you have questions, please come up or, yeah, cool. Cheers.
particularly in with black background and white things, and that's also the environment. I'm going to show you some demo code as well. So that might be a little bit difficult to see if you're sitting in the back, so you might want to move forward. I've tried to increase the scaling of of my screen as much as possible. So, but now you have been warned. We have room here in the front. All right, so I just gave another talk, and I just need to reset my brain a little bit to see what is this one about. All right, got it. All right, so back in the 2014, 2015 timeframe, I was asked by one of my recurring clients to come back and help them out as a freelance software developer. I'd done some work for them before, and then I went on to do other things, and then I came back because they wanted my help with some stuff as well. And they've been pretty busy while I was gone. And this team was a team of very skilled developers. So they had lots of great things that they did. And one of the things that they did while I was gone was that they'd enabled continuous delivery. So I learned a lot about continuous delivery from these people. So that's sort of like the organization they were. They were really good at what they were doing. But this talk is not about continuous delivery. It's about another interesting thing that they did, because also while I've been gone, they've implemented a locking system in their production system. So whenever the production code was running, it would log to. I think they used this elk stack, as far as I remember. So we started, I started helping them, creating new features and so on. And once in a while, when you create new features, you inadvertently create bugs as well. So sometimes, we would get bug reports. This happens. It was a pretty good code base. We actually did a lot of things, or they had already done a lot of things right. So we didn't have that many bugs, but they came up from time to time. And then I found out that if the bug was precise enough that we could identify when things went wrong, and sort of how which part of the system went wrong, we could usually find just from the bug report, we could find the logs, the log entries that related to that particular behavior. And from that, it turned out that we could always get an understanding of what went wrong and reproduce the problem based on the logs, the understanding that we gained from the logs. And that turned out to be repeatedly an experience that we had. So I thought that was interesting, and I couldn't really. It was very pleasant to work with, because it took a lot of stress away from understanding defects in the system. You sort of you go and look at the logs, and you look through the logs a little bit and say, okay, now I pretty much understand it. I can reproduce that as a unit test or things like that. So when I went on my own way, after the engagement ended, I couldn't really stop thinking about what was it that made that logging, such a useful thing, because they didn't log a lot of stuff. Actually, they just logged the right, they logged the stuff that we needed in order to reproduce problems. So I thought that was interesting. Did they know something that I didn't know, or did it just turn out that they were lucky? And these people were really skilled, but to be honest, in this particular instance, I actually think it turns out that they were lucky. There were circumstances around how that code base worked and the entire environment that it was running in, where it was quite obvious that there were things you wanted to log, and they went ahead and did that. But I still couldn't really shake the idea of what's the right amount of logging. So based on that experience with having this very nice, stress-free interaction with just enough logging, I thought you can actually apply a method to that. So this is what this talk about. It's about what to log, and also a little bit about how to log. I'm actually going to spend most of the time on what to log. So usually when I visit other organizations, so not the one that I talked about right now, but other organizations, code often looks like this. So you have a lot of code that is sprinkled with liberal use of log.debug and log.warning and log.info and whatever else you might have. And there's so much stuff going on there that it's noise that actually makes it hard to understand what the code is actually doing. And we should probably just spend a little time, discussing what it is that we're looking at here. So this is, one of my patented online restaurant reservation system demos. It's not patented really, but I've been using this this kind of demo application for a long time. It's one of those things where you scroll, you find a website or you use an app and then you fill in some details about the reservations you'd like to do, and then you can press the submit button. And this slide shows you how long I've been using this particular demo scenario. So I like to reuse my slides, so I copied that in. So I've been doing this for many years now. But the point is, this type of system, what we're looking at here is you press the submit button, it creates a JSON document, it posts the JSON document to an HTTP service somewhere. And the code that we're going to look at is the HTTP side of things, so not the client code that actually does that, but the code that receives that JSON document. That's what we're looking at here at the moment. There's this post method. It takes a DTO. That's basically just the data from the JSON document, and then it does stuff with it. But you almost can't tell what it is that it's doing because there's all of that logging stuff going on. So I don't think code should look like this. I'd like code to look like this. So this is more easy to read because there isn't all of that noise. Write code like that. But then you might say, well, yeah, but Mark, you just remove all the logging. So we need logs. You can't just remove all the logging and say, just because it's more readable, you can say, let's throw away all the logging. That's not what I did, actually. This code, it turns out, actually logs. We'll get back to how that works later on. Before we do that, I think we should just talk a little bit about, why do we actually log? Because there's more than one reason. As developers, we'd often think of ourselves first. So we think, okay, so we can do various things where we log debug information or other things that enable us to troubleshoot things, when things go wrong in production, and that's logging for our own purposes, which is fine. But there are other reasons as well. So maybe other departments would like you to log other types of things. So maybe the business, for example, would like you to log things that are important to them, what we typically call key performance indicators. So stuff like how many sales are you having, or how many page views, or whatever else you think might be interesting. And if you're operating in a domain where you are covered by law or regulations, you might also be required to leave behind an audit trail, which is also a sort of logging. So there's at least these three wide reasons why you'd like to log. There might be others as well, but I actually can't think of them. But that sort of thing, I think, captures most of it. But what they have in common is that you have a running system, and that running system produces some output that you can sort of peruse at your own leisure at a later time. It's typically to some sort of out-of-process system. So if we define logging that broadly, that's all logging, and that's pretty much. It turns out that it doesn't really matter that much, which of those use cases you have. So it's probably clear that we don't want to log too much, because if you've ever tried one of those turnkey solutions where you basically can click a little button or download some sort of framework, and then it will instrument all your code, and then you can try to run that in production. You probably know that it generates tons of data very, very quickly. If you log everything, that's not really practical, because it's going to generate so much data that you probably can't fit it on your storage devices, or if you're running in the cloud, you don't want to pay the price for that. And also just the act of logging everything that's going on in the system is probably going to slow down the system. So there's a limit to how much you want to log. On the other hand, you also don't want to log too little for obvious reasons, because if there's too little information in your logs, you can't use it for troubleshooting. Maybe you're not compliant with the regulations, or the business doesn't feel that it has good enough insights into what's going on. So there's also logging too little. So obviously what we want to do, we want to log just the right amount of data. So this is almost like this fairy tale with with a girl who comes into a house that is empty at the moment, and she's trying out all the food that's left, and she's trying the beds and so on, and some of it's just a little bit too much, and some of it is a little bit little, but the middle thing is just right. Okay, so that's what we're aiming for. So obviously for that reason, that kind of logging, we're going to call that Goldilocks, or Goldilogging. Okay, So what does that actually mean? So we sort of need to figure out, okay, so what is Goldilogging? So what to log? So the key lies in repeatability. So this is sort of like a theme that we've seen in software development for the last few decades, is that repeatable builds are interesting. That's something that we actually want to strive for. Repeatable deployments is the thing that we might want to strive for. So what we are going to do here is we're going to look at something called repeatable execution, and that's the term that I just made up. But the idea is that we should be able to repeat that the execution that happened in production, based on what's in the log, and we can sort of replay that afterwards. And there's a method to the madness, and we can start at looking at code like this. So here we have two integers that are being added together. X and y are two integers, and we produce z, which is another integer from that. So first of all, would you log something like this? And it seems a little bit odd to say adding x and y. But on the other hand, you may not know what x and y are, because if this is something that arrives from outside of your system, it could be the user who's entering, in a user interface, they're entering two numbers, and then you're adding them together. I don't think it makes much sense to log that you're adding them together, but if they're arriving from outside of your system, it makes sense to log what the values are. So you could sort of think of that as sort of like a variation on that. At least log what x and y are. That might make sense if they're external values. But at least we could say something else. Would you log what the result is? It doesn't make sense if you know what x and y is. This is entirely redundant, because if you know those two numbers, you can always just recalculate. You can run the calculation again in order to get z. You don't need to actually log what z was, because it is repeatable. All right, so this is a function. This is a very simple mathematical function, x plus y. And in general, mathematical functions have this quality that you can always just repeat them, and they always produce the same output. That turns out to be a really interesting quality of functions in general. It's one of the many reasons why functional programming is such an interesting thing, because we are working with functions, and we really like these things called pure functions for a lot of reasons. So we can learn from functional programming in terms of what do we have to log and what don't we have to log. So in functional programming, we really like these things called pure functions. A pure function is a function that has some extra qualities associated with it. So one of them is determinism. The same input will always produce the same output. That's what we just saw by adding numbers together. Or in general, that works for mathematics, but it also works for a lot of other things. So if you want to reverse the string foo, that is always oof. And such and going on like that. So you can actually write a lot of complicated, complex behavior as pure functions by just being deterministic. That's one side of the coin. Another thing you need to do is you need to make sure that there are no side effects. So side effect is something that changes the observable state of the system. So sending an email, or deleting a file on disk, or creating a row in a database, even repainting the screen is actually a side effect, something that a pure function can't do. So it's worthwhile being aware of pure functions have a lot of nice qualities. When they have these two qualities, there's a lot of other niceties that sort of follow from that. It makes the functions much easier to unit test, and also you can repeat the execution. So there's a lot of nice things about that. But on the other hand, we need to understand that since we can't do side effects, we can't really do anything that changes the state of the world. And in a philosophical sense, all software exists in order to change the state of the world. At least it exists to make money for some person, and that's also changing the state of the world. So we can't really do anything useful if we can't do side effects, and also having something that is non-deterministic, like generating a random number, or reading contents of a disk, or getting the current time. That's non-deterministic behavior. We can't do that with pure functions as well. So it seems quite limiting. And it turns out it's not actually that limiting, but there will be a residual of things where we need state changes, and we need non-deterministic code, and we call those things impure actions. So it's not that in functional programming that we can't do impure things, it's just that we want to favor pure functions because they're easy to unit test, they're easy to reason about. It turns out we don't need to log what happens inside of a pure function, because we can always just run it again. Whereas the impure actions, they are non-deterministic, they may have side effects, so they are more difficult to work with. So we'd like to minimize the use of those things. So that's sort of like the general idea. So if we're looking at a little bit of a piece of C# code like this one, for example, so I'm not assuming that you're a C# developer, but if you're familiar with that sort of C-based language, you can probably follow along here. You might ask yourself, if we're trying to validate whether the DTO is valid or not, is that a pure function or not? And you can't really tell at this level of abstraction because C# or Java or TypeScript or basically any mainstream language, even F# doesn't allow you to actually make that sort of decision. So in order to answer that question, you have to go and look at the source code in order to actually look at it and say, does it do any sort of non-deterministic behavior? So this is a very simple example, just to get the point across. So the protocol here is that if we return the empty string, that's sort of like an error message, and an empty error message indicates that there's no error. On the other hand, if we return a string that's not empty, that indicates an error. That means the DTO is not valid. So we might ask ourselves, are there any side effects here? And it doesn't look like it's sending email or changing things on disk or anything else. So there's no side effects. Is it deterministic? Well, it's not relying on on any sort of random number generator, or it's not reading from disk or anything like that. So yeah, it's actually deterministic. So by looking through the source code, we can determine that yes, this is actually a pure function. But we have a problem, and that is, if we might have a stakeholder that comes by later on and tells us, well, your validation code is fine, as it's not wrong, but it's not capturing all the things that might, that we might want to reject. So, for example, if people are posting, trying to create a reservation in the past. That doesn't really make any sense. We can't accept a reservation in the past, so we should consider that to be invalid as well. And you go and say, okay, so I can deal with that. I'm going to change the code a little bit, and I'm going to say if the date is less than datetime.now, I'm also going to consider that an invalid date. Now, this turns out to be non-deterministic because if you have code like this where you say the input is completely known beforehand, and then you run the code. Now, if we're trying to make a reservation on the 20th of January 2020. As you can tell, the slides are a bit old now. Something happened in 2020 that sort of made me not being able to actually run this presentation back then. But if you're running this code on the 19th, you'll get just an empty message, meaning all is valid. And then if you run it 2 days later, you're going to get an error message saying this is an invalid date. So the same input, but now the output is different. So that's considered non-deterministic. So that's a bit of a problem. Determining whether things are pure or impure is actually not that easy. Well, you can go and read the source code, and in a very simple example, the one that I just showed you here, it's sort of fairly obvious. But if you have a lot of code and your code calls some other code that calls some other code and so on, the thing about purity or impurity is that it's transitive. So if you have something that calls impure code, the caller is also impure, and the caller of that is impure, and so on. So it's difficult to actually identify that. So it'd be really nice if there was a tool instead of using our own brains for that. And I have good news and I have bad news here, because the good news is such a tool does exist. The bad news is that it doesn't exist for any of the mainstream languages that you know. So C#, Java, TypeScript, Python, JavaScript, even F#, Clojure, whatever. Such a tool doesn't exist because the tool is a language. And there's more than one language, but sort of the biggest language that does this thing, that actually can make that distinction, is a language called Haskell. And I'm not assuming that you know anything about Haskell at all, so I'm going to give you a very quick crash course in how that actually works. So Haskell uses its type system to make the distinction between things that are pure and things that are impure. And with that type system, you can actually, if you've defined a function to be pure, and then you're trying to call an impure action from your pure function, the code's not going to compile. So that's basically how it works. So you're using the type system in order to determine whether things are pure or not. So a crash course in just reading type or function signatures in Haskell goes like this. So on the left-hand side, you have the name of a function. So I am pure is the name of a function. The 2 colons is basically just a delimiter from between the name and then the type of the function. You can think of that as a method signature, like in C#. But and you read those from left to right. So the input is on the left-hand side, and you might have more than one input, but here we just have one. And then to the rightmost side, you have the output. And these are types. So we actually, in this case, we have a type called input, and we have another type called output, just to make things a little bit more explicit, a little bit explicit. So this is a pure function. And it's probably easier to see how that is a pure function if I show you what an impure action looks like. So you can see the impure action looks almost like the pure function, except that it has this little modifier called IO. So if you have this modifier that's at this IO modifier, it means that's an impure action. So by order of elimination, if that IO modifier is not there, then by default, things are pure in Haskell. So you have to explicitly say that things are impure, otherwise they're just pure by default. So that's basically how you can distinguish, between impure actions and pure functions at the type level, which is pretty nice. You might then ask yourself, okay, so if you were doing this in Haskell, if you wanted to validate whether or not a reservation is in the future, if you did that in Haskell, how would you go about solving that problem? And here's just one way of doing it. And again, I don't expect you to actually be able to read the Haskell code. It's not really important. Just focus on the two top lines, which is the function declaration. So we have this thing called validate reservation. That's a function. And then I ran out of space, so I had to move the type declaration to a new line. That's possible. You can do that. So you see here we have more than one input, but the output is something called either string reservation DTO. And don't worry if you don't understand what that means. The point that I'm trying to get across here is we look for the IO modifier and we don't find it, and that means this is a pure function. This is basically how that works. So how do we solve the problem of looking at the current time and seeing whether the reservation is in the past or in the future? Now, it's a really dumb primitive solution to that. We just pass in the value that represents what time it is right now as an argument to the function, and then the function just deals with that value. So translated to C#, it might look like this. We have a now argument, and then we're just checking on that, and that's a pure function. It's a very common thing to do in functional programming. And you might say, okay, so that's cheating, or some people might say that breaks encapsulation, and I argue that it doesn't, but that leads into a discussion of what encapsulation means. Or you might just say, but Mark, aren't you concerned that people may call this function with a value that's not datetime now? They may call this function with the value that is in 2030, or a value that is in 1980, or something else. And basically you can say, well, I'm not concerned for a couple of reasons. First of all, there's no side effects here, so it doesn't matter what they do. And also, I'm not concerned because I think that's actually an advantage, because that means instead of just running on the system clock, you can now perform simulations. So you can write unit tests that will test what's going to happen if I run this code in 2030, or what would happen in other sorts of circumstances. Or you can use your data from your logging system to say what actually happened yesterday when this code ran. You can pass those values in, and that enables you to perform simulations, and that's repeatable execution. It's basically just it's one of those many benefits that just fall out of pure functions, because you can always do that with pure functions. So that's considered an advantage. So it's not cheating. It's actually a very good thing to do it this way. All right. So I'm not trying to suggest that you should now go and throw away all your mainstream code bases and rewrite everything in Haskell. Now, if you want to do that, please hire me to help you. I would love to do that, but that's not really it's not my agenda here. What I find Haskell really interesting for is as a thinking tool. So I use Haskell for proofs of concept. So for example, if I want to learn, I have this online restaurant reservation system, and I'd like to write as much of it as pure functions, and just only the things that cannot be pure functions, I'll need to sort of isolate those and treat them differently. But I'd like to know in a system like that, what's impure, what's essentially impure, what can I not get away from being impure, and how much stuff can I actually do as pure functions. So writing a prototype in Haskell will enable me to sort of answer that sort of question. So that's what I did. And again, I'm not expecting you to know any Haskell, so I'm just going to briefly walk you through some of the type signatures here. So in the code base that we're looking at the moment here, this is basically my domain model. So this is where I model, what a reservation looks like, what a valid reservation looks like. This is how I make decisions about, whether or not I can accept the reservation or not. So here we have a little bit more of a sophisticated version of a validation function. And again, if we're looking for this IO modifier, you will notice that nothing here, even if we've, I've split this in multiple lines, there's nothing that says IO here. So this is a pure function. And we can sort of scroll down this, this file here and look at just the function signatures, and nowhere will you find the IO modifier. And that means this entire domain model here is actually written as pure functions. And we'll get back to this try accept function later on. This is sort of like the core decision logic that makes use of a lot of those other functions, in this file. So when I post a JSON document, it ends up calling this try accept method that then makes the decision: can we or can we not accept that particular reservation? And again, you'll notice, the output, the output type here looks really horrible. If you don't know what that means, that's really not something that I'm going to try to explain to you in 2 minutes, because I can't. The point is, there's no IO modifier here, so it's a pure function. So that's nice. It's nice to know that you can write a lot of actually all the business decision logic as pure functions. Now, on the other hand, it turns out that interacting with something like SQL Server, this is actually saving things in SQL Server. That is not something that is possible to do as pure functions. These need to be impure actions. Basically, anything that performs IO is impure, hence the name of that modifier, IO. So you can see it's sitting here. This is an action that inserts a row into the database. We have other things down here. Read reservation, this reads a single reservation, or it tries to read a single reservation. It says IO right here. Read reservations is a query that gives us a collection of reservations back based on a predicate. Our criterion, and it says IO here. So we have a clear distinction between things that are, impure and things that are pure. And it's nice to know which bucket things need to fall in. So there's that point. Now, I did oversimplify things a little bit when I said that this is the way you distinguish between pure and impure. There's actually a generalization of that impurity here, where sometimes you'll see things look like this, where it says monad IOM, and then there's an M, that M refers back to the monad IO. And if you see that M modifier, and the M modifier refers back to something called monad IO, that is also impure. This is sort of like a generalization of that IO modifier there. And don't worry if you don't understand it, it's just that, that's the sort of stuff that we go looking for. So we can see down here at the bottom, I have this little, this is sort of like an interpreter, and we can get back to that in a little while. But this is basically, it takes a little domain-specific language and runs an interpreter over the database. And you can see this sort of example here, monad IOM, and then the M appears over here. So that's an impure function, impure action as well. So the way that you basically, you have these pure functions, and the pure functions can't call into the database, but then you still need to do the database stuff, which is impure. So how do you sort of compose those two things together? And you do that at the entry point, basically. So it also turns out that doing anything involving the system clock is also impure because it's non-deterministic. So you can again see this monad IOM here, and so on. So what I've done here is that I've created some code that can enable me to sort of interleave pure code with impure actions via a set of interpreters that are all running and being impure. And then what I can do is I have this thing called log clock, which is also impure, but it's sort of like a wrapper around actually accessing the system clock. And what this wrapper does, it just logs, whenever I'm doing something that is an impure action, it's writing that information to a log. And the same thing goes with this thing called log reservation. It's just wrapping around the actual access to the SQL Server, but it's logging all the information. So it's sort of like the decorator design pattern. Right. Okay. So let's have a look at that as well. So this system is actually an entire system. It's just a very thin slice, so it's sort of like a proof of concept. But it actually it does work. It can do HTTP traffic. It can save in SQL Server of all things. getting Haskell to talk to SQL Server was kind of interesting. I had to send a few pull requests. I sent some pull requests in 2019, and they were just merged last week, basically. So I think the original maintainer of that system had other things to do. So what I'm going to do here is I'm going to start the web server. I'm going to need a connection string to my database. I'm just running the database on my local DB here, so I can't remember the syntax of that. So I'm just going to I've kept that in a file. I'm just going to put that contents in my clipboard, and then I'm going to run the application. So let's see. So it's not that it's anything secret. The contents are right here. I'm using integrated authentication, so there's no passwords here. So now the server's running. It's running on port 8080. So now I need to figure out a way to post a JSON document to port 8080 on my local machine. So I'm going to use another terminal for that. So I can use curl. That's my preferred thing. Do yourself a favor if you're doing any sort of HTTP work. Use curl. It just makes things easier because curl is always around. Someone told me yesterday that curl is actually running on the Mars rovers on Mars. I'm sort of working. It's getting my head around. Okay, so what's the ping time of TCP/IP from Mars to the Earth? It's like 28 minutes or something like that. So how does that work? I'm not sure that I understand that. Okay, so what I want to do is I want to post to a resource called reservations. I'm going to need to give it a content type. I'm going to need to tell it it's application/JSON because otherwise there's a little bit of content negotiation going on there. And then I want to write my JSON document. So the way it's designed, I need to give it an ID. The ID needs to be a GUID. So let's see if I can do this and then like this. So I need to create a new GUID. So I can use this thing called UUIDGen. UUIDGen. So that's just going to create, every time I run this code, it's just going to create a new GUID if I've done things correctly. I'm going to need a date. So I'm just going to use the date of tomorrow, so 2022, 06/03, and at 1900. And I'm going to need a name for the person, name for the reservation. So we're going to say Il Burrows is going to make the reservation. We need an email address for Il. So that's going to be ilbows@example.com. Like that, and we need a quantity. That's the last thing. And we'll try to make a reservation for 2 people. Does that look okay to you? Did I forget any quotes or things? No. Okay, let's try it out. It's always a little bit stressful here. Okay, so it says 200. Okay, so it looks like it's worked. So just as a sanity check, we can go. I actually have access to the database sitting here in SQL Server. So if I go and refresh that, we should now see a row in the database. So if this demo had been running, if I'd been doing this in 2002, you'd be very impressed. But you can have an HTTP thing that actually ends up in a database. But that's really not the point of the demo. The point of the demo is that while this happened, the system logged all the impure actions. So where do you always put your log files? On the desktop, obviously. This is just proof of concept code, right? So in this case, it's looking like this. So this is basically just something that, this is a format I choose to use because that's machine readable to Haskell code. It's basically just sort of like serialized Haskell code. But what we can see here from the entries is that, the first thing that happened is that, part of the system, asked for the current time. There's no input to that question because you're just asking what is the current time, but then the output was this particular value. Then the system asked, made a query against the database, read the existing reservations, using this particular date as input. It got, the empty collection as output because there's no prior reservations in the database. Then it, called this method called create reservation, and it also logged what the input was. And if we scroll to the end, we can see the output is nothing. This is called unit, but it basically means void as output. And then I also logged the entire HTTP request and response. So that's why you're seeing a lot of escaped strings here, because it's sort of the strings that I escape within strings and so on. So that's a little bit confusing. But that's basically what happened. So what I can do is that I can start, let's see, on my Haskell prompt here. I'm going to stop the web server, and I'm going to start something called GHCI. So GHCI is a REPL, read, eval, print loop, where I can just ad hoc interact with values in Haskell. And again, don't worry too much about the syntax. It's more like what can you do with the values here. So there's a little bit of color going on here, and it's quite busy to look at. So I'm just going to simplify the prompt a little bit here. So I'm just going to say it's going to look like this. And I'm going to clear the screen here. So I'm going to do something like that. All right. So the first thing I want to do is I want to load that file. So again, don't worry too much about the syntax. There's a built-in function or built-in action called read file, and I just need to find my file on the desktop. So it's something like users mark desktop log.txt. All right, so that reads the file. So if we don't see any exceptions, that just worked. If you're wondering what L is, L is just the log. It's just the contents of that file, and it looks quite unreadable here. So we want to parse it. We want to interpret it into something that are actually proper Haskell values. So the way that I can do that, I'm going to create a new value called replay data. And the way that I'm going to do that is I think I have a function or an action already. This is a function that's called replay. Let's see, replay, something like read replay data from a log. Okay, so if we look at what that looks like, replay data, that looks a little bit more, it's a little bit more readable. Still quite, abstract. But we have all the information, and now they're actually Haskell values. It's like, if you've done this in C#, now you actually have C# objects. This is a collection of objects, basically. So, for example, if we're interested in, if we want to see what was the reservation that was actually logged, I'm going to need that later on, so I'm going to call that R. So I can get the head of, that's just the first element in a collection of something called observations of post-reservation, from that replay data. So there's my reservation. So let's clear out this as well. It gets a little bit busy. So let's start here again. So let's just, this is the reservation that is in the log. We've now passed it, and I have access to it. So if I'm wondering what happened, I'm not really, but just, if in case I am, I talked about this function called try accept before. So I can try to ask, what's the type of that? So when I go :type, I'm not trying to run the function. I'm just, basically looking at the type of it and saying, what's the type of it? And that looks really complicated. But basically what it turns out is that it needs a reservation as one of its input arguments, and then it needs something else. And those something else is the seating duration. So this restaurant has a seating duration where you have a table for a couple of hours, and then you have to leave the table because there might be other people. And then we also have a table configuration. And I can read that from a config system that I have already. So I do that. So seating duration is something called a nominal diff time. That is basically the same thing as a time span in C#. So that's just the duration. This is 9,000 seconds. That's 2.5 hours. Tables, it's the table configuration from the restaurant. So this restaurant has 4 tables. It has a table for 2, it has a table for 4, for 6, and for 8. So I thought that was easy to remember because that becomes important a little bit later on. So now I have those values. So what would happen if I try to call, I can sort of ask the type system, if I try to call try accept with the seating duration and with the tables and with the reservation, then I lost the, and then it came back. Okay, so what it would give me is this horrible looking thing here, except T of blah, 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 blah. And you don't need to understand exactly what that is, except that it is a pure value. It is not something that is impure. But the pure value actually describes a little program in a little DSL, and you need an interpreter to run over that program in order to figure out, what's actually going to happen. This is how you interleave pure functions with impure actions. And what happened when I ran the actual code was that interpreter then went and interacted with the database. But what I can do now is I can define another interpreter that instead of interacting with the database is going to replay what happened in the logs. So I have another function here called replay. I think it's called replay, yes. And it takes the replay data that we already have, and it takes one of those except-t horrible-looking things, and then it produces a pure value and something called an either value that indicates whether it's a success or a failure. That's basically how that works. So you notice all of these are pure functions. There's nothing that says I/O here, so the replay would be a pure function. So what we can do is I can find the try except here, and I can say, let's replay that with the replay data that I have. And I just need to put a little symbol there. And it produces the value right of nothing. So that basically just repeated the execution that happened on the server based on the log data. And if it seems a little underwhelming that it just the output is right of nothing, it's because this was trying to save something in a database, and that's all about the side effect. And the side effect doesn't really produce any output, or it can, but we didn't do that in this case. So there's no output. It just means things went well. There was no output. Fine. Okay. So the point of this is, again, it's not that I'm not trying to convince you that you should write all your production code in Haskell, but it's interesting to do those kinds of proofs of concepts because we learn something about what is pure, what can be pure, and what has to be impure. And what we've learned here from this little proof of concept is that the impure actions in a system like this one is, first of all, the database, and the system clock. Now, this is not surprising. If you've done this sort of exercise a couple of times, you will know that databases are always impure because they involve I/O, and the system clock is always impure because it's non-deterministic. But there might be other sources of impurity as well. But in this state of the application, that's basically what we have to deal with. So in order to have, in order to figure out what to log, basically what we've learned so far is that we don't need to log what happens inside of a pure function because we can always just rerun the function. But the things that we can't just rerun is all the stuff that's impure because that is non-deterministic or may have side effects. So that's the stuff we need to log. No more than that, but also no less than that. We need all the impure things logged, but that's also going to be enough. And that's sort of like what that little replay demo also demonstrated. So what we can now turn our attention to is once we know that, we can think about, how do we then do that in a sane manner? And not like this. All of those log statements that are sprinkled all over the code, that just makes the code really unreadable. So that's not what we want to do. So I also wrote the code in Visual Studio in C#, so we can now try to have a look at that. And the post method that I think is more readable is this one here. So it doesn't look like it's logging, but it is. And the way that it works is, you'll notice, for example, that it's not accessing datetime.now. It's doing something called clock.getCurrentDateTime. And if you know the .NET API, you think, what's that? I've never seen that before, because normally you do datetime.now. So if you go to the definition here, you'll find that this is actually a method on an interface called iClock. And I define this interface because I know the system time, the clock is non-deterministic, so I need to hide that behind an interface. So that's one thing. Also, it turns out that the database interaction, so for example, if I'm reading the reservations here, if we go and have a look at that, that's another interface. This is a repository interface that defines read reservations, and it also defines a method called create. So you probably, most people will probably have some data access that's hidden behind an interface already. So that should be sort of, not surprising. And if we want to see, what kind of classes implement that interface, first of all, we'll find something that is not surprising at all. We have a class here called SQL Reservations Repository. And if we just try to scroll a little bit, we'll see we have some SQL code actually sitting here. This could also be based on an ORM. It doesn't really matter, but it's just like this is the thing that actually talks to SQL Server. So that's not surprising at all. Now, it turns out, though, that if you at other things that implement that interface, there's another one. There's one called Log Reservations Repository. And this one also implements the interface, but it does that by taking an inner one and wrapping around that. So this is a design pattern known as the decorator design pattern. And if you're wondering, okay, so what's the inner one? We can go and look at the place where we actually create this thing, and you'll notice, not surprising, that the inner one for log reservations repository is actually that SQL thing here. But it might be something else, but that's the way that I usually configure those things. So inside of the log is sitting the SQL implementation. So what happens here with the create method, for example, is that I take the reservation, then I log that this interaction takes place, and then I call inner.create. And this is a void method, so it doesn't return anything. The same thing goes with the read reservations thing here. I'm calling inner.read reservations first, and then I have the output of that. I log that this interaction took place. What was the input, what was the output, and then I return the reservations. And I do the same thing with the system clock. We can very briefly look at that if we're interested. There's a system clock implementation that just delegates to datetime.now, but then it's decorated by this log clock that, not surprisingly, just logs that we accessed the current time and what the time was at that point. All right, so I have the system running already, so I should be able to go and interact with it and see if that actually works. So it's running on a different port, and I just need to figure out what that port is. So it's sitting right here. And if you're wondering why it looks like there's an error at the moment, it's just because this is a proof of concept. It's a very thin slice through the entire system. So this system actually doesn't support HTTP GET requests. It only supports a post, and that's why we see that this 404 error here. This is entirely expected. I just needed the port number. So I can try to basically reuse that request from before, just with a different port number. Maybe just to keep things a little bit more interesting, we should change the name here. So instead of having L making the reservation, it will be her brother Rain, and so we will have rainbows here instead of elbows. So if you remember the table configuration of this restaurant, it has table for 2, table for 4, for 6, and for 8. So now we're trying to make another reservation on the same date, on the same time, for 2 people. Now that should still be possible because we have a table for 4, maybe not good business for the restaurant, but if they don't have any other reservations, that could work. Now, what I did here is that I actually I introduced deliberately a little bug in the system. So if I try to actually run this, it doesn't work. Oh no! You'll notice here it says internal 500 internal server error, couldn't accept. What went wrong? There's a bug in the system. How can we troubleshoot that? If only there were logging. Let's see, where do we put the log? We can just put the log in the file there. You can see there's this thing called log.txt here. So yeah, we actually logged what happened. That was fortunate. Let's just clear this and have a look at it. So what's inside log.txt? Well, in the C# demo here, I decided to do that as a JSON document instead of this Haskell code instead, because that's easier in C#. But the idea is the same. We have all the data that we need in order to figure out what actually went wrong. So what I can do with this is I'm going to move that log file to my unit testing library. So booking API.unit tests, and I'm going to call it repro1.txt. So I'm just moving the file there. And then if I go and have a look at my code in Visual Studio, if I scroll down and have a look at my unit tests, you can see repro.txt is sitting right here. And one thing I actually want to do straight away is I'm just going to make that an embedded resource. And it's basically because I actually want to read the contents of that file. And when doing that from a unit test, I think it's easier to just make it an embedded resource and read it from there, because otherwise you need to manage actually moving files and copying files around and making sure that they're cleaned up afterwards and so on. Your mileage may vary, but that's what I usually do. So I'm going to add a new test class here. I want to be able to reproduce this problem here. So I'm going to add a class called repros. And make it a public class. I'm using xunit.net, so I have to decorate it with this fact attribute here. And let's say public void, I'm just going to call this repro1 as well. So this is the first repro that I want to do. So the first thing I want to do is just load the log from that embedded resource. So I did cheat a little bit, so I have an API for that. So I'm just going to say, okay, I'm going to load repro1.txt from that embedded resource there. So L, let's call it log. That's a little bit easier. So L is just a string, and you recall that that string is actually a JSON document. Now, the next thing I want to do then is I want to have a system under test. I want to be able to create an object and test this. And I also need to read the data transfer object, the DTO, from the log. So what I can do here is I'll show you how this works afterwards. But I have a little API for that as well, where I say load the reservations controller post scenario. And then what it does, it returns back the system under test. That's my reservations controller, the one that has the post method. And then it also gives me a DTO that was passed out of that log file. So that's the reservations DTO object. And I can now exercise my system under test. So I can say post that DTO. So again, I'll remind you the DTO is passed from the log file. And then, what's actually supposed to happen, this actual here is something called an action result. So I want to say that this should be assignable from something called an OK result, because I would expect this to work. I also know that it didn't. I'm going to need to import a namespace here. I also know that it didn't. So if I try to run my tests now, I would expect this one to fail because that was a bug in the system, and it does. It actually does fail. So it says, I expected an OK result, but I actually got an object result. And if you try to sort of examine that object result, you'll figure out, or you'll find that it actually contains a 500 internal server error with the message couldn't accept. So that's how that works. So we now have a nice repro of things here. And I can show you in a little while exactly how that works. But the nice thing about having a repro is that now you can actually start troubleshooting. So I deliberately made this little piece of sabotage here. So I know where to go and look for it. So the defect is actually sitting around here. So I'm just going to add a breakpoint just to prove a point here. So I can add a breakpoint. I can go back to repros. I can decide to go and debug that particular test, and I'm going to wait a while because that takes some time. Let's see. I think we hit the breakpoint now. So what's happening when we're running this test is that it's using the log information to replay what actually happened, and then at this point we are going through a loop and trying to find the index of a table that can fit the reservation that we're interested in, and we find the index. It's the first table in the collection in that array. So the index is 0. So we actually did find it, but then, so we say, okay, so we found the table. That means we can remove the table, down here. We can remove the table of that index. Oh no, it returns false. And we have an off by 1 error here. So it shouldn't have been, less than or equal. It should just have been less than. So now we understand what the problem is. And I knew that because I actually deliberately introduced this bug. But the point is, you can actually use the debugger, or you can use all your other troubleshooting skills, because now you have a deterministic repro of the problem. And then once you find the problem, you also have a nice repro test that you can then run and see that you now fixed that that particular defect. So how does this work? Let's go back and have a look at the repro. So what happens inside of this method here is that it takes the JSON document and it starts to parse that JSON document, and it looks at all the different operations that it encounters and sorts them out into various different collections, and then it creates some replay implementations of those interfaces. So it's probably easiest to understand the replay log. the replay clock, sorry. So when you initialize the replay clock, you take all the observations that you've seen in the log file of, whenever the system is asking for the current time, you put that in a collection. This is an IEnumerable of date time. You pass that to the constructor of the replay clock. It creates a queue out of those because they should be in order. And then every time we call get current time, that's the interface method. We dequeue one of those values that comes from the log file, and we return that. So that's how it's replaying what happened. And the same thing basically is true for the repository. It looks a little bit more complicated, but basically the idea is the same. When we call read reservations, so read reservations might be called with more than one date time. So the first level of data that I have here is a dictionary where I index into the dictionary and say, okay, I want the entry in that dictionary that corresponds to this particular date. And I may have seen more than one observation of that particular date. So inside of that dictionary entry, there's a queue because there might be more than one observation of that query. And then again, I dequeue one of those values, which is an IEnumerable of reservation, and then I return that. So these two things, the repository here, which is a replay repository, and the clock, which is a replay clock, I now pass them as dependencies. I inject them into the reservations controller. So when the reservations controller and all sorts of other things that might want to interact with those things, when it calls methods on those classes, it replays what was in the log. So that's how that works. Right. Okay, so we're pretty much done. So just to summarize, we really favor pure functions because pure functions, we can always just repeat that execution to get the result. If we know what the input to the pure function is, then we also know what the output will be. We can just run the function again. So we want to have as much pure code as possible because all the stuff that happens in pure code, we don't need to log that. What we need to log is the impure actions. In this case, we saw one example was the system clock. We want to log all of those accesses. And also, we are accessing the database. We want to log that as well. So the way that I do that, I'm using this decorator pattern where I'm wrapping the actual implementations in another implementation of the same interface that then performs the logging, the decorator design pattern. So basically, in order to do this, you sort of need to move towards a functional paradigm because otherwise you're just going to have a lot of impure and pure code interleaved. But if you can do it, here's the recipe. So first of all, identify all the impure actions. So in this case, it was the system clock and the database. Model those actions as polymorphic types, an interface or base class, because otherwise you can't use the decorator design pattern. I just stick with interfaces. So make interfaces out of the database access, make interfaces out of the accessing the system clock. If you have other things, if you need to send emails, you need to hide that behind an interface as well. If you want to generate random numbers, you need to hide that behind an interface. And once you've defined all of those things that are impure, behind an interface, use the decorator design pattern to, log from the decorator. And that means when you're using one of those polymorphic types, there's no logging noise in your actual code. It just happens automatically that, whenever you're doing something impure, it's being logged to a log destination somewhere, and then profit basically. Use the logs to enable replay. So it's just to make sure that I get my point across here. It's not that I actually recommend that you create one of those replay machineries that I just showed you here. The reason why I showed you this replay stuff is just to get the point across how deterministic it actually is if you have the right amount of information in your log. Now, I didn't do that when I worked for that company that I talked about 7 or 8 years ago. What we did was basically just look through the logs, and then there was always enough information in the log that we understood what, we could get an understanding of what the problem was, and then we could go and write a unit test that reproduced what happened at runtime, maybe using some of the data that we could pull from the log. So it was more like an ad hoc process, go and look at the logs, maybe take some copies of the things, write a repro, and then run that one. So it's not that I have, this fancy machinery. This was just to get the point across. But that's basically what I have in mind for this talk. If you want to see more of the details of how that works, you can go to blog.plur.dk and find the archive, search for repeatable execution, and I have a little blog series with 3 blog posts that walks you through that and shows you some more of that code. So if you're interested in that, you can find it there, and it's all free. You can also go and buy some of my books if you'd like to. And in Code That Fits in Your Head, I talk a little bit about that, but actually most of the details are on the blog, so that's probably where you want to go. And I'm out of time. That fits perfectly because I'm also out of slides and out of content, so thanks for coming.
Hello? Hello, everyone. It's right on time. I think we can get started. So welcome, first of all. It's my first time in Copenhagen. And today we're going to talk about, or I'm going to talk about, and I hope that you will have questions at the end, about gRPC in .NET, especially. My name is Irina Dominte, still scurtul, my maiden name on social media. I'm from Romania. I'm a software architect, and I love .NET. .NET is the only thing I coded ever with. JavaScript doesn't count this. But from time to time, I teach .NET. Twice a year, 5 months, I'm teaching .NET to people that are trying to switch careers and get into software development. I often blog, and I have a 10-month-old daughter that is at home right now. And for me, it was very hard living. So if you have kids, you'll know what I'm talking about. So, first of all, we cannot talk about awesome architectures, microservices, serverless, and everything between them before we talk about monoliths. And I'm going to ask you, who here loves monoliths? Yay. Nice. I'm glad to see that I'm not the only one in the room. So why do we love monoliths? Or at least I'm going to talk and tell you why I loved monoliths 14 years ago when I started. Well, first of all, I remember having big solutions, and when I pressed the build button in Visual Studio, I could have easily have gotten to take a coffee because the build took that much. And I didn't have to worry about every kind of dependencies in code. Everything was there. I think we used some kind of dependency injection mechanism, a DI container, but more or less everything was there. You needed a class, you went ahead, you instantiated that class, used the functionalities and everything that class provided. And of course, it's easy to start. But, well, things kind of look like that. First, there was web forms, then there was ASP MVC, different versions, and now we have things like that. JavaScript apps to worry about, or many APIs to worry about and to orchestrate. And we need to admit that everything right now is distributed. We need to adapt to the times, and these times are like that, distributed. And of course, us as developers, we want to work in shiny technologies with the latest technologies out there, or preview versions and so on, and try out new things. And things that are, let's say, easy to manage, one front-end app and one API that sends data to the front end, easily becomes something like that. We have one front-end app within whatever JS, and several backends that, of course, backends talk with several databases, or maybe with other backends. If we look from the high level with a high-level view, things might end up being like that. We do not have single stacks anymore. We might have apps that are written in Go or whatever language that suits the business needs and solves a specific problem. And of course, those apps talk with third parties' APIs. Because we don't need to reinvent the wheel. We integrate with something. We integrate with, I don't know, maybe payments API, because we do not want to handle the payments ourselves. And we would use, for example, Stripe, right? And we build on top of that the business functionalities, the domains that we have. And now, when it comes to talking from one application to another application, server to server, you might say that we have a REST for everything, right? And let's face it, who here ever implemented a REST API? Okay, fully REST API? You see? Yeah, the deal is we often build APIs that sense JSONs as response types. But in fact, those APIs are not really REST. And they follow some basic principles from REST, but are not fully, entirely RESTful. Because to implement something RESTful entirely, it's hard. Yeah, you need to have HOIS. You need to worry about what are the next steps to build your API as being a state machine and so on. And we do not want that. We usually want something like, okay, right-click, create new project, deliver a database, send some data over over the response. Okay? So now, when we have certain APIs, we have a client, and that client might not always be a front-end app. We usually have to point-to-point communication between back-end apps, right? And what do we use? We often use HTTP clients. Whether those are named clients or not, where we simply, I don't know, create and make calls to post or to get data from one side to another. Well, between these two parties, there is a process that is called content negotiation. That is done under the hood. We kind of do not care about, or not that we do not care about, we care, but we do not think about when we implement things. So that content negotiation mechanism will look at the format of the request, the payload, the format of the payload. With that, and on top of that, we will need to do error handling. We will need to take care of retries, right? When you issue a call, you wait, and that response doesn't come. What do? Do you retry? How many times? How often? These are things that we need to handle. There isn't anything out of the box. So another thing that we should care about is authentication. How do you do that? Who does authentication? What we look at when we're doing authentication? So if we look at the other way around, API to API, what happens when one of the models changes? For example, you issue a call, you expect a specific format, like an object of different properties, and those properties change. How do you handle that? I know, let's say those properties are completely removed. You always need to plan for forward or backwards compatibility when you're talking API to API. So I'm going to say, OK, now, what's wrong with REST? We use it, we implement it, we brag about that we have RESTful APIs. So REST, as a concept, forces us to be chatty. Forces us to be chatty with the teams that implement the front-end apps or the APIs that we're integrating with. So let's move on a bit. Since we all agree that we're not implementing fully REST APIs, but we send data. I don't want to offend anyone, because I admit I'm always doing that. I send answers over HTTP in a JSON format. So I'm calling that RESTful endpoints, because those might look as being REST in terms of naming and so on. I'm using proper verbs. But beyond that, I'm not willing to spend time to invest in that. So here we go, remote procedure calls. What is a remote procedure call, or an RPC? I heard that is a concept that has been around since the 70s, since people started programming things. They will try to make two systems or more systems look and behave like they're in the same place, like they are one whole. So let's have a look at some code. If we were to look at this, we might say that, hey, every line of code here, it's in the same system. It's a monolith. You use things from there, right? Because the code, it's, to a developer, something that is approachable and instantiable and is there. But how about if I tell you that, for example, for processing a payment, there is a network call, even if the code pretty much looks in the same code base. So this thing makes us, developers, to forget that there is network involved, and we might tend to abuse these calls, right? And we put a lot of work to our DevOps to orchestrate and monitor these microservices. So an RPC, as a general concept, will make the code look local, because it has a call a method look and feel, right? You're just calling methods, those look like are there, but it's prone to errors, because one of the purposes, it is to make the network communication transparent. Transparency means that you can look through that, and you might not tell there is something behind it. So making a distributed system behave like a monolith. That's pretty much how I envision this. So, okay, enough with the talk. What is gRPC? It's been around in .NET for a while. Started in 2001 as being Google's stubby project. Fast forward, in 2019, we got gRPC in .NET with .NET Core. And since then, there are a few improvements, a few more improvements, that we can put our hands on. So, gRPC, as a concept, is contract-based. You will have a file that will define your services, something that might be rather similar to what we have in WSDL files, if I'm allowed to compare that has operation exposed, and those operations are, let's say, fancier than the WSDL exposed ones. So we will have no-code references when we will use gRPC in code. It will use HTTP2, inherently faster, out of the box, no need to do anything. It's there. And the serialization of gRPC messages, it's smaller because it uses a binary serialization. It is available in many languages, which will allow us to talk language agnostic with different other languages. And it will do code generation out of the box for us. So point and click, add the proto file, code generated for us, and you just build on top of it. So now, if we were to look at the client-to-server communication, and the client, it's an API, we get this file in between. And this file is a contract that settles the thing between the consumer and the party that serves the data. So, the proto file. The proto file has a specific syntax, proto, that kind of looks like this. You need to specify the syntax, the version of the syntax. You need to tell it, okay, what is the server namespace that will be generated for you? In this case, will be my first gRPC. The package that will be generated, and then you need to specify what will show up in the WSDL file to make a comparison between that. So what we have here, it's a service named Fibo that exposes one method named compute Fibonacci of an input type, requested number in this case, and returns a Fibonacci result, the result of it. The method is RPC, you have the keyword mentioned in there, and using this approach, you can define your own methods that you want to expose to developers. Of course, the input and the result needs to be a gRPC type, and in this case, a message. Each message has properties that get translated to C#, and each property in there will be assigned a number, and that number is not a real assignment. I mean, in 32 number, it's not equal to 1. It's the order in the field because it's binary. And kind of, that's it. So defining such a proto file, you'll expose different service methods to the outside world. Okay, hang in there. I have a lot of code to show you. So with the theory, you have 4 types when it comes to gRPC. Some call them modes, some call them types, but are different, basically 4 ways of calling the methods or methods behavior. Unary, which is similar to what we already know, request response, server streaming, client streaming, and bidirectional streaming. And looking separately at each of them, we have unary, request response. There is an issue, someone that initiates a request, that request goes to the server receives it, and it answers back with whatever response it is. How such service exposed will look, something like that. You already saw that in the proto file example. gRPC, server streaming. So there needs to be one party that initiates the request. The server receives the request, but sends back several chunks of response. How do you implement this? Is by adding stream keyword. I hope it's visible in there. Stream keyword to the result. So it gets an input and sends several things as an output. gRPC client streaming is the reverse of it. It's still a party needs to initiate a request, And that request is comprised of many chunks. Those chunks are being received and interpreted by the server, but the server sends one thing back. So many in, one out. How do you write that? Is by adding the stream keywords near the input of that specific RPC method. Imagine this is useful, for example, when you need to upload large binary data. You can chunk them and you can upload them, or maybe if you have to upload many small files, or a different scenario like that. Or maybe why not collect data from different sensors that you know that are pushing very often and very many things to a system. Okay, and bidirectional is a combination of the two, where the same party initiates a request, sends several things as part of the response, and sends back and receives back many chunks of the response. Okay, how you write that? By adding the stream keyword between as an input and as the result. Okay, so let's see some code, and then we're gonna get back to the slides. Okay, first of all, I'm gonna try to maximize this and hope that it's visible to the upper rows. Okay, what do I have as an example? I have a server, a gRPC server, that implements it and exposes the 4 methods that we have. And then I have 4 client-side apps or console apps that are consuming the services that I'm writing. So what do we have here? First of all, we have the proto file that has a service. And inside that service, we have 4 methods exposed, written using the methods that I'm exposing there. And I'm having 2 messages, one named very inspired request, just to mimic the request that we all know, and response to mimic the response that we all know. On top of that, I need to show you something in project file, the libraries that I'm using. First of all, I'm using gRPC, gRPC ASP.NET Core, and protobuf. These are the NuGet packages that you need to install. And one thing you need to add when you use Visual Studio to create the gRPC service, this bit will be added by Visual Studio. You have, hey, I have a proto file that can be found in this location. In this case, it's living inside the same project, but you can add the path in here to move in upper directories or in the different repositories, but you need to make sure that the file with the proto extension is reachable by your current project. So this way you can extract the logic and the interface definition language, the proto file, outside and move it in a different repository and make every other service access to that. And here, there is an option to say, hey, this is the server app, behaves like a server, or there is a client app, consumes the specific proto service. Okay, what do we have here is the greeter service. As you'll see, it inherits greeter base, but that bit I didn't write. It was generated for me. As I told you, gRPC will do code generation for you. And the only thing that you need to do is to come and write on top of that. So basically override the methods that you're exposing to that proto file. The logic that I have here is something very easy. Say hello is, okay, something that you get in, that type of request. And each of these methods will have a response type in terms of message. So this response is that type that we define here. It has a field name message. And in there, you will always find something that is called server call context. It's similar to HTTP context that we know from Web API or ASP MVC. And on that context, you can take different things. For example, the claims for the user, if you have authentication on that. So you simply use context, get HTTP context, and you'll have info in there to grab. Or if you want to get the user that is specific to that, you can use that and get the user. Another thing that, well, you can use with gRPC is to install certificates and do authentication using certificates. It's very easy to do that. It's everything wired. You just need to provide everything that is needed. So pretty much this is it. I'm going to show you how it works. So we take it one by one, so unary, and I'm going to show you the console app. It's a simple console app, right-click, new console app. And what I did was to install the libraries that are needed. ASP.NET Core, ASP.NET Client. This library provides a specific way of accessing gRPC services. But in here, unlike the server app, I'm specifying, hey, this is the client, is not the gRPC server. So it will behave like a client. And one thing I want you to look at is the path to the proto file, that it points to an upper level server protos grid proto, which means it points in here. But if we were talking about actual add reference in code, we won't have any code reference. I'm going to show you here. So into dependencies, we have only the packages that are necessary for gRPC to work, but no add project reference as we used to do in different other technologies. Okay, so with that being said, in program CS, we use channels, and we say, hey, I need to access a gRPC channel that it can be found at this address, port 5000. I don't want to use anything credential related, so I'm going to use insecure here. And then you're going to create a client. It's something very similar to HTTP clients that we all know, and pass that channel through, and then create an object with the request and the property value, and just wait for the response, okay? So I'm going to run this, and I'm going to run this in a console. So in here, I have a console app that will run the server application that will expose gRPC operations. It's building, and hopefully everything works. Okay, you see it started to listen on to ports 5000 and 5001. And on the right-hand side, we're going to have another window that will run the unary project, so the console app, that will send a gRPC call. And we're going to look about what's happening. So sending NDC through gRPC, and we have one response back. Hello back from the NDC, from localhost. We put the port there also. And on the server side, we will see that something happened. A request happened. And that request was made using HTTP 2 on localhost 5000, greet, say hello, and was of MIME type application gRPC. And it was a 200 status code. Okay? And one thing to look at is that it's a post request. Each and every time you issue a gRPC request, it's a post. You don't have the concept of sending a GET, even if you actually get data, but the verbs in the traditional way are only post. Is the only thing that you can use. Okay, so using post, you kind of say goodbye to things that are get verbs are getting you, like caching, maybe. So, right? So you'll need to find additional ways of implementing that. Okay, getting back to the code, we're gonna get back to client streaming, and the approach is the same. So I basically created a new channel on localhost. It's insecure because I don't care about security stuff, right? What we're gonna say is, hey, I'm gonna have a for loop that goes to this value, and I'm gonna send the index to the server, and I'm gonna get a response back. Okay, and I'm gonna wait for it to finish. So, client streaming. Using the same approach, left-hand side, right-hand side, huh? Okay, the server is listening and waiting for responses. And in here, we have the client streaming. And I'm gonna run the project. And let's see what's happening. You see, things are running on the server side. And the server side gets requests with specific types, the I from the loop in there. And on the calling side, I got only one thing back. And that one thing back being the last value that was sent to the server. So server gets things, many chunks in, and sends one response back to the calling party. Okay, let's move on. But not before I tell you something. Status codes in gRPC are different than the status codes that we know of. We have 200, we have things like 404 top level, but if you want to really deal with gRPC codes, then you need to catch exceptions, and those exceptions are of type RPC exception, and then deal with the types that you have. It's called status codes, but if you look at it, there are different values, like aborted, already exists, unavailable, cancelled, data loss, invalid argument not found, out of range. These are not point-on-point to status codes from HTTP protocol. These are specific to RPC, and you need to treat them accordingly if you have a business case for it. Okay, next example. We're gonna have a look at the server streaming to follow the same approach. So again, create a channel, create a client, and this client, I don't know if I mentioned, it's done by the protocol itself. And we're gonna have something like, okay, again, send something to the server, to the calling party, and expect the response. I'm gonna do the same. Server expects something, and in here, I'm gonna run the app. Whoop. Fingers crossed. Okay, you see, server is streaming things to the client. So the client gets many things as responses. On the server side, you see there is the server stream method called. The call took that amount of time. And also, you'll notice things like this. On the client side, it found some trailer values. Because in gRPC, the concept of a header is rather mimicked. You cannot attach like the proper header to an RPC call, but you can add these kinds of things that are called trailers, which are basically key value pairs that you attach to the request. Let's see how these look. Okay, greeter service, server stream. You see there is the metadata, entry, header, and you just see add a key and a value for it. And this is how you're mimicking proper header per call, right? So it's not at the request level, it's per call. And you simply attach that to the context, as you would do in an HTTP classic context. Cool. Another thing that it's worth mentioning that whenever you're issuing a call to a gRPC server, you have the possibility of sending different options, like cancellation tokens, like deadlines for those requests. So I'm gonna save this, and I'm gonna try to server streaming here. I'm gonna run it again, and now hopefully, what? Yep. Thank you. So server is still out there. And you'll see something like greeting timeout, because I put an amount of time that is very short. So cancellation token passed in from seconds, 5 seconds, and it's passed in here. But also, as you see, the deadline parameter takes precedence, and I added 1 millisecond, so no way I could have beaten 1 millisecond, okay? So you have the deadline. So you can put yourself everything that makes sense for a specific business need. Anything else? So looking at the directional, it's pretty much the same. but you just issue a request and you wait for the results. I'm going to use the same approach, bidirectional. This will work. Okay, so sending and receiving. It happened very fast because I added an index that it's finishing at 10. So sending these values and receiving these values. But do not get fooled about this because the order is not right. So in this case, we got it ordered, but in some other cases, you might not. So don't get fooled. Okay, getting back to the slides, there are a few things that I wanted to mention. Call them gRPC internals. Status codes, as I mentioned, they're totally different about HTTP, so not the same. HTTP exception, you need to catch that and filter what type of exception you have. You can add interceptors to intercept gRPC call and to introduce yourself in the call, like in the pipeline, as you would do with the middleware in Web API. You can have response headers, trailers, the mimics, and you can tweak some things. And some of these things are, for example, enable detailed errors. This is by default on false. You can have things like what is the message size to prevent overposting or large chunks of data to be added in there. You can add the response compression because that's important in specific scenarios. And if you want, you can specify the compression algorithms in there. gzip or whatever you want, you can add your own compression provider broadly or your own if you have one in there. So these are the things that can be configured, and I advise you to configure this if you use gRPC. And of course, security-related things. We cannot talk about web if we are not talking about security. What types are supported? So pretty much everything that we would need in a web app at the channel level, at the connection level. And you have all these, right? So you can attach them. So what are the benefits, basically, of using gRPC versus a different thing? So I would say the performance in size, which is performance and size, is important because it will be, depending on the response type, about 80% smaller with gRPC than a traditional JSON in there. It's awesome for polyglot environments, but for point-to-point communication, it will use a network just a tiny bit because it's performant and it's smaller. It's contract-based, and it has malware payloads, HTTP2. I don't know about you, but for me, it's hard to keep up because I just learned about HTTP2, and now they're talking about HTTP3. And one thing about gRPC is that it's prepared for HTTP3, so they say. Of course, supports different streaming types over a single connection. And yeah, in .NET 6, it's there. So I'm going to get back a bit to the code. OK. Sorry, wrong timing this time. OK. What gRPC should do awesome in .NET 6? Because it does, and this is what I wanted to show you. Transient fault handling out of the box. You can configure some things that I'm going to show you to manage this. And also, another thing is client-side load balancing out of the box, which I think is kind of impressive because it does it by itself using an algorithm that you can specify, and you do not need another tool to do that. So let's have a look. In extras, I'm having this. So this is a client, right? That consumes the same server that is in there. So talking about retry policies, we can configure things like what is the default policy, default retry policies. For example, you can say that it has two max attempts to retry and do a call. And initial backoff, maximum backoff multiplier, retriable status codes, and you need to specify here which is which. And in this case, and of course, you can also have hedging policies. I'm not going to go into that because there are more experimented people that are talking about specific things. But thinking about this, like we do not need to use poly, and it's out there for us to use. I think it's awesome, and it's worth implementing. Another thing is related to load balancing. For example, you can retry throttling, you can load balance things, and you can do it in several ways. For example, if you know the ports that will run on the server side, you can have a static resolver factory that will say, hey, I'm listening to these specific ports, and you give it an array of balancer addresses. You have a local host and the port numbers in there. There is also a way of using DNS, but I didn't have the proper setup to try it. I assume it works, but with static for a demo, it's just fine. You add the service collection, you pass the resolver factory as a singleton, and then you can use it. And you can use the same. For example, for addresses, you need to use this policy, static. My example host, this is a simple string. It has no impact on when you know the specific ports. You say that, OK, this is insecure because we do not deal with that. But when it comes to service configurations, you say, hey, for load balancing configurations, use round robin as, right? Or there is another option to use first available, but that won't be necessarily load balancing. OK, and what I'm going to do here is just make a call, OK? And to demonstrate this, I'm going to leave the server, this option, and I'm going to start a new one. I was hoping to make sure I'm not getting myself into trouble. I'm going to do this. Open a new console. Here. Of course, it won't run. gRPC, CD, and stuff like that. And I'm going to say, hey, run this app using these URLs. And I'm going to use 5002 as a port. And fingers crossed, this will run a different instance for the server. And it's up and running. And it's waiting for requests. OK, and now I have two server instances running, 5000 and 5002. If I go back to one of my clients and start, hopefully, if I run this, I will get back from a specific port that is configured statically. And if I run it again, fingers crossed, maybe I will get from the second one. And I'm going to try that until I get something back. What? No, this worked. No, because it works like that. It worked like that before the talk. So, only 5000 and here. Please. Come on. Something is happening. OK, why? Let's see what I did here. So I was trying this 5000, 5002. OK. What is the port that is running? OK, trust me by my word. Apparently, I didn't pray enough today. To the demo goes 5002. Listening. I'm going to maximize this. OK, now listening. Why? Oh, I think I know why. I'm trying to run something that is not the project because I kept them so separate. OK. It's called extra gRPC, right? And now .NET Run, fingers crossed. Yay! Okay. So sometimes it's not good to keep things that separate. So you see 5,000 and 5,002 because was the client basically that was having that static policy configured in there. So why not? Okay, another thing that we can look at is the DNS resolver factory. I'm not going to run it because, as I said, it's not tested to work. So you have DNS resolver factory, and what we'll do, you'll change here from static to DNS, and hopefully it will work in here. So the thing with this is that, well, if you have pods that are spinning up, this is very nice because maybe you'll know the port and it will be picked up and round-robin. Okay, cool. Let's see what we have in there. Client-side load balancing. I find it very, very nice. So you have DNS and static, and you have two options with pick first or round-robin, or why not? You can implement your own resolvers. I don't know, maybe you have an algorithm like try on the first server available 3 times and 2 times on the next one available and so on. But there are still downsides when you're talking about gRPC. And downside would be that there is still a temporal coupling. It's not a silver bullet, and it's not the same as using messaging, like a service bus or a bus or something like that, where you won't need temporal coupling. You won't have that. You might forget that there is a network involved because the code is so similar, so friendly to you, have a method that you're calling, and that's it. But in fact, there is a DNS call, resolve, and so on, and you get the data back over the network, right? It's not human readable, and I would say until now. It was a major issue until, I don't know, 6 months ago or something like that. The binary format, it's binary. You cannot scramble to the binary and understand what's in there, right? But fortunately, there are tools and people that are developing tools. And one of those tools, it's Postman. Have you used this? Yeah, right? It's my favorite tool in the world to make API calls. And it has something that is very nice. For example, you can say, hey, I have a new gRPC request. It's still in beta, but it's there for us to use. And you'll see that you need to enter the server URL. I'm going to try to maximize this a bit. And let's see, because I have here localhost 5000. You say, hey, I need to search a way. I'm going to minimize this to show you. How do you load the proto files? Because that proto file is the thing that exposes things to the outside world. It's the WSDL, the new WSDL. Okay, you can use server reflection. I tried it and it doesn't work right now. Proto file definition from local file or from URL. If you're using on a production environment, it may be URL. What you'll do is just click here, go to your local file, blah, 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 and find the proto file that you're having. Fill some info, and then you'll get the methods that are available and exposed. And you can actually issue requests, and you can invoke them. You see? There is a message, hello back, hello from localhost. What happens is this creates a message for you automatically. You can generate example message, and it will generate something like that. And in here, if you invoke him, the method, you have hello back with the whatever generated value from localhost and the port. So this way, you can actually test your gRPC services, thing that was impossible until a few months ago. The similar way, you can use different methods. Let's see. It says that it's streaming, but I'm pretty sure that this has that deadline in there. Okay, I'm going to use Where is streaming? Because it doesn't show. And streaming. Received. In the end, it received something. Okay. And another tool, well, I don't think you're coming since you're here from a Java world, but apparently this is the tool popular in the Java world. It's called Bloom RPC. You can find it on Git. You can install it, and it's similar to what Postman does. You can import things and expose these things, and you can invoke them. Bidirectional, you just press play, and you get things back. Hello. And it supposedly runs. Okay. Cool. Another thing that I want to show you, but it's in .NET 7, but it really worth looking at it, is transcoding. Have you heard about gRPC transcoding? What it does? So basically, if you are in gRPC, well, you have post, you're tied to a post request, and you have all these tools to look at. But you can do a very nice thing. You can also expose your gRPC service as over the browser by itself. So how it looks like, it's still in preview, so I'm sure this will be changed. So you'll need to do a thing like that. You will need to implement basically copy and paste from a source. James Newton King is the author of this. So you might search its GitHub. There are two proto files, one called annotation proto, and one is HTTP proto. So you need to copy paste these two files in a Google API folder. This is, I'm sure this will be needed to be done right now, right here, until the final version it is, because you cannot go to GitHub to download two files to make this work. Okay, so greater service is the demo, the standard one. In programs, yes, you will need to add JSON transcoding over the add gRPC, and of course you need to have a NuGet package, namely Microsoft ASP.NET Core gRPC JSON transcoding. Okay, and with this being done, you will need to go to the proto file that you're interested in and say, hey, I am exposing an RPC method named sayHello that gets an input of type hello request and returns a hello reply. But I want to get the option to call this as a GET request using this specific URL. And what it will do, I'm going to set this as a startup project and run it. I had done this morning, and you notice how I ate a G transcoding. I didn't have my breakfast, apparently. Okay, so this is running. And if you want to access things like, I'm going to copy this to make sure it works. You see, hello name as a response. And the only thing that I did was to add the two files. I'm sure that won't be needed to add those anymore. The package and this little guy here. And it's pretty neat, because in this way you can consume gRPC services as normal RESTful over HTTP ones. And this being done, I think it's very important to have a look at gRPC, because it's very, very powerful. Okay, gRPC versus REST. I don't know if I convinced you that gRPC is worth looking at, but in comparison, from the developer perspective, an HTTP API, let's not call it REST. It's REST source focused. Everything that we have in there, it's a REST source. It embraces HTTP semantics, verbs, status codes, and everything that we have. It has loose coupling. It's text-based. We can look and read the specifics. And RPC is action-based. You look at it as calling a method, embraces everything that we know as developers. It has tire coupling. Even though you are not adding a code reference, as you used to do in HTTP APIs, but you have that proto files. the proto file is basically the thing that couples you to everything. So as long as you're sharing that between your microservices, you have strongly coupled things, right? Even if it's a file. And it's binary. And it's awesome because now we have the tooling to look at the binary files. So all in all, when and why gRPC? Because it's a new shiny thing, maybe, and we have microservices, and we move data from one side to another with HTTP client calls. So why and when? I would say that when is when, right? Point-to-point communication, microservice to microservice, point-to-point. Then use gRPC. I would use it, at least. And one thing that it wasn't possible until now with gRPC was the support for Azure. In Azure App Services, you couldn't host it. But now they said that, okay, that is solved. You can use app services and host your gRPC. So these are the points that I think are worth mentioning. It decouples code in the ways of not creating spaghetti references in there. You have the proto files that you will need to take care of and distribute across your microservices. And I think you will need some more tooling around that and testing. Because I think developers will tend to use gRPC files as being backward compatible. You know, the versioning that we do in HTTP APIs, you know, and we remove fields or we add fields, but we need to take care of compatibility. Well, with gRPC, it might be a bit harder to do that, and you'll need to invest in testing. So if you were to ask me, a future down below will be no more hunting for documentation, even though REST as a concept should save us from a lot of reading, because it would be intuitive and so on, but it's not always the case. There will be no misinterpretation of status codes. I mean, okay, how many of you are still using 422? Or bad requests, right? And there will be no more data parse errors. Think about this. In gRPC, you have that file that specified the messages, their formats, their data types, and as long as you have that, every other service that uses that file knows what type to deserialize or serialize, right? So there will be no more, okay, this is an open API specification that receives this response, and so on, right? So the mismatch between the data types or the responses and so on won't be that hard anymore. So distributed systems are all about trade-offs. There is no silver lining, there is no silver bullet to solve it all. There are specific business cases that could use that, or could use some other technologies. But as long as we know about the technologies, we can make an informed decision, right? So that's why we should know about the tools. What are the next steps? So have a look at gRPC Web. It's still in development, and I would say it's a different kind of gRPC stuff. HTTP 2 and 3, of course. Protocol buffers, if you have the syntax, and you can look at the syntax. gRPC curl, if you prefer more command line approach. Postman, because I'm sure they will end up on being not beta with gRPC, right? Bloom RPC and 2books, if you want to have a look. Anthony Giretti has this, and Mark Randall was here, and he wrote something about gRPC for WCF developers, if you're familiar with that technology, and it will be easy for you to move one concept to another side. And thanks for listening. I'm here if you have questions. You have here some resources, and here the QR code will bring you to the resource GitHub and everything like that. So thank you. I'm here.
out enough, but I think this is better. Welcome, everybody, and thanks for staying here. I hope you thank me later when I'm done. Today, I think it's a great moment to be alive. It's a great moment to experience what's happening and going on today in AI and machine learning. It's quite exciting. It's, well, started quite a few years ago, like 25, at least to what really counts, which is Garry Kasparov was beaten in 1997 by, I think it was IBM's Deep Blue. I think it was that one. It was not deep learning yet, but it was quite made for education. That was the biggest moment in AI and pushed a lot of investments there. And then a bit later on, we have been beaten at our own game, starting with the most complex game on earth, Go. That was 2015. I think it was AlphaGo that beat the world champion. And a bit later, we were beaten at the even more complex game on earth, StarCraft. And some years later, I think it's 2020, 2021, we have reached parity on human comprehension at reading, at image, and even listening audio. And today we are applying AI to almost everything. If your company or you're not applying AI, you are getting behind. That's it. Today we are getting to take a look at two ways to do this. One from the cloud in Azure, where we can scale, compute, and train models, and then take that model and use it in our machine learning code with ML.NET, in .NET code, in C# or F#, your choice. Why should you listen to me? Well, you're here, so you don't have any option. Apart from that, my name is José Luis Latorre. I'm originally from Spain. I work at Switzerland at the moment for a very Swiss company, Swiss Life, and I'm leading the .NET user group at Zurich, which is really fun. I love community. My Twitter handle is GOSLAT, which comes from the three first words of my name and my last name, and my GitHub as well. All the slides and everything I will show you, code, is already on GitHub, so you can take it from there, all the slides, so you don't need to make pictures. I made it easy for you. Also, I'm a Microsoft MVP. I talk a bit, they listen, they gave it to me back last year. It's fun. And I work as a dev community lead and software architect. Don't see that logo. It's about developer community inside the company, which is fun. Try to motivate my colleagues that are not doing open source to do more open source and talk. Today we had, well, this session we had 3 colleagues from Swiss Life, which is quite cool. Well, one is not technically, he works with us, which is Michael. He's doing amazing things with GraphQL. But before going there, I'd like to get to know more about you. No. So I want to present in full screen. I want to get your mobiles off and activate the poll. How are you? You need to be close, you need to Zoom. Let me know. It's 2 days. I don't know how many of you did already the workshop or participated in a workshop. Anybody? I did not. 1. Well, I guess the rest are pretty tired. 2. Okay. You are surviving. Oh, fantastic. Okay. A bit tired, good. Come on. You can do better. Coffee's free. Okay. A bit tired. All right. I will not make your code. That's for clear. I think we're done. So, still not. So, between tired and good. Fair enough. All right, let's go to the next one. Otherwise, we are not ending. So, I want to know if, do you know a bit about machine learning, Azure machine learning concretely? How to do that with the platform from Microsoft for the cloud? Well, one of the platforms, right? Nope. Play a bit. Use it for work. Wow. Who's that person? Who uses it for work? Nice. 2 persons. Cool. What do you think about the build news and upgrades? They are cool, right? I don't think so. Some of them are ugly. All right. So, at least no master. That's good. Otherwise, I would ask you to come up. And last but not least, do you know machine learning.net? Do you know it? have you play a bit with it, you work with it, you are a master of it. 2, 3, all right. Okay, good. All right, so you know what that's pretty good. So what we are going to take a look today, I hope this works, yes, is first we are going to do a quick refresher on AI. What's AI? Very, very simple, but I think it's worth a bit. We are going to take a look at Azure Machine Learning. What is it? What is ONX? Does it ring a bell? You know what's ONX? These two persons that know a bit about Azure Machine Learning, you're working with that, probably you know. And then how to generate an ONX model, or how to export an ONX model with Azure Machine Learning, and then what is machine learning.net, some concepts about it to understand it, because it's not the easiest one, and then how to consume a model with Azure, with machine learning.net. So we will train it in the cloud, deploy it in a way which is transferable, and use it in our code that we can deploy anywhere that .NET runs. Let's get it done. AI. AI was born in 2015. As soon as we could code computers, we tried to mimic human cognitive abilities. So at least the human abilities that show that we can think, not all of us show that. Then a bit later, quite a bit later, on 80, we had machine learning, which is the ability of computers to learn from experience. So we could train a computer, a model, based on data, and then do what is called prediction or inferencing on this model that we have trained. That was not that good, not that exciting. There were some hiccups there. The biggest win was from what I mentioned, Garry Kasparov, Deep Blue, but that was a computer really, really made for power to beat Garry, right? So that was not that exciting. But the exciting part comes in 2010, which is deep learning, which is the ability of machines to mimic how we think and do things, to mimic our neuronal system, our brain. It's composed by neurons, so we have the concept of artificial neurons that AI is mimicking now, and they can layer them in different ways to mimic how do we think. How does machine learning work? We have some pictures, we label them, we train with them a model that we have to pick, and then the model can see the picture and determine it. Let's see again. We have some pictures, we label them, that should be a classification. We train the model, and we deploy the model, and then the model sees one of the pictures and can say, oh, that's a Bellis perennis. On machine learning algorithms, we have generally 3 kinds of models, which is supervised, unsupervised, and reinforcement. Supervised are those which are labeled, which is what we are usually focusing in and what we should start. These are the simplest, starting with one which is linear regression, which is nothing more than statistic application of machine learning on data. And on supervised, we have as well classification, either text classification, either classification of categories, or image classification or text classification. And we have as well unsupervised, which is we don't train it, we don't give it any feedback, and this is usually used for anomaly detection, as well as it can determine relations between elements. And then we have reinforcement learning. We don't label it, but we give the training model some rules, and it iterates and plays the game again and again and again. That's how the world Go champion was beaten. That's how usually robots are trained in simulations, or how they train these, I don't remember the name of the model that beat these StarCraft, but that's the way it is done. The machine learning workflow is normally starting with the data. We have something called ETL, which is extract, transform, and load. This preparation to feed the data into the training, to train the model, and then it produces the model, and that's called the training phase. Once that is done, we can deploy the model, and do what is called the prediction or inferencing. So we feed it unknown data or similar data, and it can give us the results. Nothing more. That's about it for AI refresh. We jump right away to Azure Machine Learning. Who knows Azure Machine Learning, apart from these two persons that work with it? It's a proposal, or one of the proposals for Microsoft in the cloud to deploy and train at scale AI. It's meant to bring AI to everybody, and it's really easy to use. I myself, as a machine learning aficionado, usually I don't use it too much for work. Sometimes I implemented some NLP models for natural language processing, but that's mostly it. So I learned it on my own, and I can say that it's everything which Microsoft promises, it's really that. And I would like to, you two that say that you are working with that, to hear your feedback on how you're using it. It's meant to boost your data science productivity, to increase how you experiment. Experiment is how you train. This is an experimentation, how you improve your models, and also to enable you to deploy and manage your models everywhere at scale. And it has that and much, much more. It has something called auto machine learning, which basically is using machine learning to do machine learning. Pretty cool. We will take a look at that. It enables you to have managed compute, to deploy single instances of a compute node made exclusively for machine learning, and as well to create clusters so you can scale horizontally as much as you want to train your models or to do inferencing. It enables simple deployment, DevOps for machine learning or MLOps, as well as supports mostly all the open source frameworks using a tool agnostic Python SDK, which integrates with Azure Portfolio. Azure Machine Learning has two parts. One is the backend, another is the frontend. The workspace is usually what we start with. That's what we create in the portal, in the Azure portal. Are you familiar with the portal, with Azure portal? Yes. Perfect, good. So initially what you do is you create what's called Azure Machine Learning. Before it has the name workspace, now it does not appear anymore, only the slides. And then you create some Azure artifacts, which are storage account, container registry, that's optional, a key vault, insights. And with that, the workspace can do its work. You can link some services, external, like data stores, compute targets. You can use your own computer for training. What's the point of using the cloud, where you can scale as much as you want and then use your computer? Doesn't make any sense for that. You can do that with ML.NET. And enables you to deploy very quickly compute instances and clusters. We will take a look at that. And it manages everything you need for managing your assets, your experiments, your machine learning in the cloud. Managing experiments, the environments, pipelines, data sets, models, the endpoints, and now since build, I think it's components as well. Have not played with components. Have you played with components? Somebody? No, yet. And then we have the UI, which is called the Studio. Not to mislead with the previous version, in 2015, there was the first release, which was Azure Machine Learning Studio. Now it's Studio, the classic, which you cannot create an instance of it anymore in Azure. It's now deprecated, which had only the UI designer, the drag and drop experience, which we will take a look. The Studio has a set of Azure Cloud Services, Python SDK, and 3 different flavors that we can create models, and then enable us to prepare the data, build the models, train the models, and do everything that we need as a data scientist. This environment is meant for data scientists or developers that want to do some machine learning. It makes it easy for us. Let's take a look at the Machine Learning Studio and cross fingers that it works well. So first, I'm in a resource group here. Can you see that properly? Should I make it bigger for the ones behind? It's good. Okay. Good eyes. Then, I don't want to create that. I go to home. I create a resource. I put machine learning. If it goes well, I click on Azure Machine Learning, and then I click on Create. Then I select a user group like this, NDC Copenhagen that appears by here, and see And it proposes me the region where I am, the storage account, key vault, application insights, and container registry by default is none. And then I could review and create and click create if I wanted, but I have it already created. If I go to this group, I click on this element with this icon. This icon is the logo of Azure Machine Learning, call one. And here, that could be considered administrative. Here, I could give permission to the team that has to work with this instance of Azure Machine Learning. If I didn't say it, it's meant for collaboration. So you can collaborate and work together in creating machine learning models and see what your peers have worked. And you can annotate in their notebooks. It's pretty meant for collaboration. I think the annotation is like 3 or 4 months old. You can check some properties, some alerts, metrics, diagnostics, and logs. But to go to the meat, we can launch a studio, which is a complete different portal. I think it's, I'm not wrong, it's ml.azure.com. And once we click there, it loads a workspace. Yeah, ml.azure.com, perfect, good. There we are. Here, you can do everything. You can change the tenant if you have more than one tenant. You could NDC Copenhagen or another, but I want to go here because here is where I have the demos. Here, we can train models, we can deploy models, we can create data sets to work and compute. The first thing you should do here is to go to compute, and in this case, start or simply create. I'm going to create a new one just for you to see. Let's say, hi, I'm a compute. I could do a CPU or GPU and select for recommended options or select all options that you have enabled. I have quite a few more because I asked for it. And that's pretty cool. If you don't have them all, what you can do, what you should do is you should like determine and select some options. I think you should make a ticket on the Azure portal. Otherwise, you have it limited. For a default subscription, you have only 4 cores, which is not really enough to use it properly. And then you click create, and after a while, it is created. It takes like 2, 3, 4 minutes, and it's quick. And I have a cluster as well. This cluster and this cluster, I put 12 machines on it, which are not bad. It's good. And then that's essentially it. You have 3 flavors. You have the home and the ability to create an author using notebooks, which is declarative computing, using Python, which you can use Markdown language, mix with code and execute. It's pretty cool. We will take a look at that. Use automated machine learning or use the designer. Then you can manage assets like data, like bank marketing data I have uploaded. It is just an import of a CSV. You can have the jobs, which is like the experiments, which are the execution of a model, which is either a designer pipeline, automated machine learning, or a notebook. And you have environments, which are ready-made environments for either training or inferencing, which are concrete environments defining exactly what you are going to use for that. And it creates simply these environments. And the models you have deployed. We are not going to deploy any, but if deployed, we could deploy them as endpoints. And there we would have a REST interface to access them. After that, you can manage the compute as well. We did that already, manage some data stores, some link services, and data labeling. Link services, I believe it's mostly for integrating with other Azure services. And data labeling, if we click on create, you will see it's mostly for classification of image or text. Yeah, we can see multi-label, or if it's image, multi-label as well. So it's mostly for doing this supervised training that we saw before, nothing more. That's it. Well, this I will skip because as internet was a bit shaky yesterday, I recorded yesterday all the demos in video, but I think it's better if we do. And we will take a look at the Azure Machine Learning Designer now. If we go to the designer, usually you click here, you enter an environment. Where you have some components, and you can drag and drop some information here, like automobile price data. In this case, I have already finished one. And this is Copenhagen Designer. This part, I think it's not that easy. They changed it. Before it was like separated and by functionality, and now is everything mixed together. This is one of the new novelties, news of build. But here we have this element that we can preview the data and see a bit the statistics of each row. For that is better a bigger screen, as you can see. Then you can apply some changes, some modifications, the ETL, like select the columns in the data set. Configure. Show parameters. Yeah. No. So here I'm excluding the normalized losses. Here I'm show parameters. Yeah, I'm cleaning all the columns. This is changing because yesterday it was like I could edit in the left and removing the entire row. And here I'm doing a split of data, one for training, other for validation. And I'm adding here a node, which is the model I want to use, which is linear regression. And here I'm training the model. Finally, I'm scoring and evaluating that. I have already executed that. So if I go to the jobs, I discard the edit. I have here the experiment executed in the compute. And once I click on the job, I can see the already defined element here. And I can see it. This usually flows from top to bottom, and the data goes to the bottom. And you can see when you are executing visually how it is going. So here I could see the missing data. I could check here, preview data. If it goes, does not take too much time. Here is 193. So before it was 205 elements. Display the data. I'm doing like 70%, 30%. And finally, train the model, and I evaluate it. And here I can see with the outcome of the training. Yep, meaning the square error, which is closer to 0 is better, etc. That's about the designer. Other thing we can do is automated machine learning, which is using machine learning to do machine learning. This part I like it. It does feature selection and engineering. It manages the data guardrails, so it can tell you if your data is in balance or not, or if it has any problem or outliers that will destroy your model. Selects the best model for you and does hyperparameter tuning, which is optimizing the model. Once it has selected several models, it does that with the models, given that you give it enough time. And then explains to you the model, takes some insights and tells you, okay, this is a feature which is more interesting, and gives you insights for it, and proposes different tasks as well, like classification, regression, and time series. Recently, we have NLP into it, which it was not before, which is natural language processing. Basically, it's a data scientist in a box. To me, it's the dream of an aficionado machine learning scientist. Essentially, it selects the features of the data, tries the different models, selects the best ones, and then does a hyperparameter tuning on them to make them work even better, and gives you an optimized model. And it does that with several models, and gives you at the end a leaderboard. So let's take a look at how it works. If I go to automated machine learning, the way to trigger it is very easy. You select a data set. I have already uploaded one. And you click next. You can create a new experiment. You can select the column, the label. The label usually in machine learning is the one thing you want to predict. In this case, is yes or no. This data is data from people that go to a bank and their existing conditions, how much time they stay in the bank, what is their job, etc. And it determines if these people will sign the contract or no, essentially. And I put usually here, it's better a cluster. And I click next. Then it determines the kind of training I want or I need. I could enable deep learning if I want. It does not need to be. And I could also select some configuration. As it is a classification, AOC is array under the curve, which is a kind of a calculus with false and true, false positive and false negatives, and determines how precise my system is. That's quite cool. And then, this is important, exit criterion, we could put like half an hour. I think here, when we do through the interface, the minimum time is half an hour. And concurrency, as I have 12 nodes, it proposes already 12 nodes. And then I could simply say next and execute it and finish it. But I have already worked it. This would take more or less half an hour, a bit less than that. And if I go to jobs, I have it ready for you. This NDC Copenhagen Auto Machine Learning. Here, I love the names that it gives. It's pretty funny. So if you don't give it the name to the job, it gives it for you, or the same for the experiment. And we can see on total, the winning algorithm, in this case, is the sum of two, which is usually called an ensemble, which is the union of two models, which is usually used in competitions like in Kaggle. That's quite interesting. And the score it got like 0.46, which is pretty high. It's like kind of a 94% precision. That's not fully correct, but then we can see the data rails. We have some kind of class balancing detection. So if we improve that part, it would be even more precise. And then we have the scoreboard that we mentioned before, the models. And for the winner, we have some explanation. We could go there, see the hyperparameters that we got, explore them a bit, and here is the score they got. We wanted another, we could explain model, this would trigger an additional job. But for this, if we look at explanation, that's quite eye-opener. Here, we can see the different parameters, how much do they affect to the outcome. So let's make it a bit bigger. So you can see that the duration, for example, of the person that is in the bank affects the outcome. So the more time they manage to get you in the bank, the more likely you are to sign the contract. That's quite interesting. And there are some things that they cannot change on you, like if this is the person employed, yes or no, and then some factors which are more on the economy that they cannot change. Yeah, Euribor, and then the age. Well, what they could is, okay, let's invite the person to a good coffee, let's have a nice talk, try to get them more in the mood, and the rate of success of getting people in will increase. That's a nice takeover if a company does that with the persons that are going to buy the product. Either it's a car, it's a contract, or in our case, an insurance in my company. Pretty cool. And then we come to ONX. ONX is Open Neural Network Exchange. It is a format that was created like, I think in 2019 by Microsoft and other vendors. One of them was Facebook or Meta. And it's meant to enable all the ecosystem of machine learning to have a unified model of interaction, to send a model and share a model. Either it's for training or either it's for inferencing. I think it's pretty cool. To me, what one thing I say in a conference last year, and it stick to me, is like Nugget for AI models. How many of you did know ONX before? 1, 2. Well, now you all know it. And basically, it enables almost now all the frameworks and components to create and train machine learning to create natively an ONX model, most of them. And some of them that do not have native support, they have, there's a project called ONX in GitHub. Okay. All right. Which has several libraries for it, including some converters. And with that, you can either use it, you have as well some optimizers, and once you have your model in ONX, you can use it in Windows, Linux, Mac, everywhere. Also in the edge, in your mobile devices, tablets, everywhere. Everywhere you can run, at least today, I will show you how you can run an ONX model in your computer and code it, basically. And also you can deploy it to Azure. So it's pretty cool. Apart from that, it's meant to use the full capabilities of your device. So it has the concept of optimizers. So different companies like NVIDIA are building optimizers for ONX. So it's really cool because it will use, if you deploy to like an IoT device for NVIDIA, you can make sure that it will use the full capabilities for executing that ONX. It will adapt to the precision, digit precision of your system where you are executing, and it will really work very fast. So let's build an ONX model. For that, let's go back to Azure Machine Learning and go to the notebooks. Here, I have already a Python notebook. Python, for those who you don't know, it's very easy, so we will not dig too much into it. But what is important, this is this kind of declarative computing, where you mix text, which explains what you're going to do, and you mix code. And the text is in Markdown, so you can check. You probably know Markdown, but it's really easy to use. You put like a hash, and then you have a title, etc. And then you put code. And then on the code, you can run all cells below, and you could execute everything. Here, to go a bit quick, I'll go quick because we have to create the model and then use it in machinelearning.net. You are importing different libraries, like this open data set for getting the taxi data that we are going to do a model. We are training a model that gets data from New York Taxi and determines with some conditions how much you are going to pay, which is good. So you don't want to be ripped off if you ever go to New York, right? You can use this model. And then we get the data. So we create a data frame structure, and we do a filter with start and initial time, and we get like some range of data. And we show a head, which is the first 10 rows of the data we got. Here we have them. And then we are building the time features here. So I'm splitting the date in month, day, weekday, and hour. So the machine learning algorithm can process it better, analyze it better. And then I show the first head. So this data is here, month num, day of month, day of week, hour, day. I'm going to remove some data that I don't need, like fair amount, tip amount, etc. So that's a bit of cleaning, and then I do the scribe that shows a bit the statistics of the data. And here we can see that some things are a bit off. So we have a fare with 0 passengers, pickup latitude of 0, which is not fully correct, and yeah, total amount, which is negative. So, and we are going to get rid of that. So we do a bit of a query. We select everybody from the range of longitude and latitude that is inside the zone of New York. And we remove the passenger count, which is, we select the ones that are greater than 0 and total amount is greater than 0. And also the trip distance, which makes sense. If we have like 31 kilometers wide in New York, we only select 31 kilometers as trip distance as maximum. And at the end, we can get rid of this data. We don't want it. And we are ended up with some clean data that we describe again to see there is no outlier. And once with that, we can do the machine learning training, which we import the Azure Machine Learning Core workspace. We create it. We use sklearn to do the training trust split. And we do like 80%, 20% with some randomized seed. And then we define what we defined before in the interface, we do now here in Python. That's the auto machine learning configuration. We do a timeout of minutes, experiment timeout of 30 minutes, or 0.3%. The primary metric, now we are not doing a classification. We are predicting a number. That's a regression. And we put everything in auto machine learning settings. And later on, we import auto machine learning and add this. One thing here I'm doing different than the demo. So this all code comes from a walkthrough that you can follow, but there are two different things that you need to do. I put that on the slides on the next slide, which you can download, and you can try that at home, which is enable ONX compatible models true, because some models are still not compatible, and this ensures that all that I'm using are compatible. That's important. Then I launch the experiment. I load the experiment, so I'm able to create the job and launch an experiment. I call it tutorial New York City Taxi, and we will take a look at it later, and we run it. And it does the same that we did. So it tries different iterations of different models and selects the best one, which I believe is this one, the light GBM. At the end, we get the results. We can retrieve the best result and try to do some prediction and get some model accuracy, which is like 0.86, which, as always, as closest to 1 is the best. Then we want to retrieve the ONX model. That is done retrieving the output and telling it that I want to retrieve the ONX model with this line of code, and I'll get it here. And then to save it. And then I'm importing the ONX converter. This is deployed already here, but this comes from this GitHub page that I showed you a moment ago. And you will need to do that when we go to machinelearning.net to use it. I tell it this is the name of the ONX model, and then I tell ONX model converter save. And when that is done, we have it here. And we can download it. And that's everything you need to do if it's not generated natively. And at the moment, I think it's the only way to do it with Azure Machine Learning. I hope at one moment the auto machine learning will generate natively. Yes? Yes.
So I guess you use this methodology to actually do more detailed things compared with the designer.
That is correct.
Yeah. And is there a way to combine it? Because you had some that actually.
Yes, there is. There is a new feature which has been released. I think it's still labeled as preview. When you go to the designer, let me show you. So that's everything I wanted to do. Then I have downloaded that part. But if we go to automated machine learning, and I go to one run job that was executed here on auto machine learning. This is the one I ran through the interface. And I click here, if I'm not wrong. Models. If I go here. Oh yeah, you can view generated model preview. So somehow this should be enabled. This is one of the features that should be enabled, and then you can see the generated model. And I believe if you go here, you can use that and maybe copy that into your notebook experience and then play with that and improve it. I think that's really powerful. Then let's go back. We have built our next model. The next thing to take amount is we should, when we put the auto machine learning configuration, so as your colleague was saying, we are doing the same that we did in the interface, we are doing in the notebook with Python. Then we have a parameter that we cannot set in the interface yet, which is enable ONX compatible model true. And when the model is built, this model is already compatible. We know it because we specified it. So we can export it as ONX, and we do so. We treat the model, and we convert it with the runtime ONX convert from the ONX converter project, which comes from this GitHub repository. Then we go to the other side to use this model, ONX model, that we have downloaded. For that, we have machinelearning.net. Who is familiar here with machinelearning.net? Has played a bit? OK, nice. This is open source. It's nothing more than a NuGet package project, which is led by Microsoft to do machine learning, but not with Python, with .NET. In this case, with C# or F#, whatever you like the most. And it integrates very well with Visual Studio. In this case, we can do both things. We can build a model, train a model, and use a model. This has a kind of weird syntax. I found it really confusing when I jump into it, which is similar. It's taken from Spark, if you know Spark, and you know what I'm talking about. Then you create first a data view to prepare the data, to collect and load the data. You create a pipeline and append it, and you have an eye estimator. With the eye estimator, the only thing you can do is feed. You can train it with the data. So you have to select the model, put eye data view with the data, and then you feed it with the data and save it or use it. And then to use the model, you load the model, you have a transformer, and with the transformer, you can get a prediction engine that you can do predict, which is, OK, give me my prediction, like an oracle. So machine learning as well has something called the model builder, which is integrated in Visual Studio. I think Visual Studio Code has something similar now, but don't know if it's officially supported. And everything is local there. But you can use some cloud acceleration in some cases, and has integration with tools and DevOps. Any .NET application is supported. And it's open source project, supports TensorFlow, and of course, with some libraries, ONX is supported, and it's really high performance. So it's even more fast. It's faster than if you do Python. So it's a good moment to know how to code in .NET. So let's see how to work with that. But before it, I need to show you Netron. Who is familiar? Who knows what is Netron? Netron is a tool from Lutz Roeder. Is enabling you to take a look and pick at machine learning models. It's a pretty cool tool. Here I have it. And then I can open a model. I open a reason. And here we have the model that we just implemented. And we can see the model properties. And we can see something that we need to be able to use it. We need the inputs and the outputs. Exactly with the same name as it is in there, and the same type or parity of type, right? You can do more things, like show attributes, which if you are into machine learning can be interesting, but this is what we need to go and do. The inputs and outputs. Is it big enough? To the end. Perfect. So here I'm mapping to the types of ONX with the perfect type, with the exact names. The exact names need to match the column name, and that's basically it. And that for the output as well. Nothing more. Yes? I coded it. There's no automatic generation so far. I know they are working on it, so they want to make the experience a bit easier, but at the moment you have to code it. It was quite straightforward, except one type that was a bit troubling, but usually it's Netron helps a lot to do that. And then on the program, what you do is you import your model. Here it is. And then you create the context, which is a class from ml.net. Before that, you have to add some dependencies. Initially, Microsoft.ml, then the ONX runtime and ONX transformer. That's these two, you need them. No discussions. Once you have that, you can use and create the ML context and create a prediction pipeline with this context. This prediction pipeline is part of a function that will return the transformer. With the transformer, we can create the prediction engine and do the predict. This, I'm also adding some input columns and output columns. And I'm adding some transform, because I want to deliver a transformer. This essentially is matching output column names to the input column names and also deliver the model of the path. The only thing I don't like from here is that I need to train it yet. So initially what I get here is not a transformer, but this one returns me a date view. And I use this, which is a ONX scoring estimator. It's an I estimator. So sorted forces me to train it, even if it's with empty data, to be able to use it. But that's the only thing, the only catch. If you do a normal model with ML.NET, you don't need to do this empty training. But once you do that, you get it, you get a transformer, and with the transformer, you can create the prediction engine, matching the input and the output, and then you simply give it some data, like day of week, hour of day, day of month, passenger count, and the trip distance. And if you execute that, to prove that I'm not lying to you, you get here the predicted fare, which is $45 and $8, which I think is cool. So, some conclusions is Azure Machine Learning rocks. I hope the people that work with it think the same. At least I had no problem with it. The only problem I had is I was updating this demo, and I think it's because of the changes in the build. I had a dependency, and suddenly my notebook was not working properly, but I only had to do update with the pip on the packages. That's it. And it was quite straightforward. If any of you try to repeat the steps, leave me a comment or issue in my GitHub, and I will put exactly the comment that I use. Because I think the images were not generated properly and were lacking some Azure Machine Learning dependencies. Usually, it's straightforward. They generate the compute instances, and they were like a charm, but they were not, like 2 days ago. But luckily, I tried that before here. Then, machine learning.NET is pretty cool. It really works really fast. I mean, if you can train a model in less than 60 seconds with more than 80% of precision. That's pretty awesome in your development computer, that is, with auto machine learning. And we can generate an ONX model with notebooks and consume it from machine learning.NET. That, honestly, is the way it will be from now on, at least until AI gains conscience. I mean, they say that in 2030 is when we will have enough computing capability to emulate a full human brain. So we will see. So this is my my GitHub, NDC Copenhagen, or simply github.com/Joslet, and you will see that right away. There is the slides, there is the code, and the links. Okay. So that was it. I hope it was interesting and you learned a lot. Mm.